this third session and of this Indo-Brazil webinar and second day. And it is my pleasure to anchor this session. So from Indian side, we have two very renowned speakers, Professor Deepankar Choudhury and Dr. J. Kumar Shukla. They will be speaking on foundations, theory and practice, theoretical studies on combined pile raft foundation, CPRF system. So they will be touching on the theoretical fundamental of combined pile raft foundation. So let me tell something about briefly about the speaker. But before that, let me give you little more introduction about India and the Indian Geotechnical Society. So yesterday, my colleague, Professor Samadhya, talked about the Indian Geotechnical Society in details. So today I will not touch too much on that aspect, but I would touch more on the India and its relationship with the Indian Geotechnical Society. So basically, India has tremendous geotechnical problems. As you know, India is a very big land. India is a big country, and we have from north to south, it's almost like 4,000 kilometers of the distance, and from east to west of India, we have another 4,000 kilometers of distance. So if you see on the northern side, we are having basically Himalayan region and also followed by the alluvial soil, Indo-Gangetic soil, which is basically nothing but a silty soil. So in silty soil, there are many problems, especially about the bearing capacity. And it's also a earthquake prone zone, so liquefaction. So all those problems are there. If you travel to the Himalayan regions, which is also there in the north and also there in the east part. So we have many problems related to landslides, slope stability, instability rather, and development of infrastructure is a big challenge, tunneling on such soils, etc. In south region, we are having the coastal region. A very long coastal region is present in India, and all this coastal region, as you know, is surrounded by soft soil. So we are having soft soil problem also. In the western region of our country, we are having the black cotton soil, which is a expensive soil. So we are, this is a special kind of soil and needs special type of foundation. So India is having a lot of applications of geotechnical engineering, and in India, research is mainly carried out through the central laboratory established by the central government. Those are not more, but maybe 7, 8. And then we are having IITs, which carries out the research, which are 21 in numbers. We have NITs, those are 27 in numbers. And basically, we are having the issue in Indian Geotechnical Society. We are having the twin issues. One is that of the quality maintenance, quality of the soil investigation, quality of the reports, and quality of the design. And second challenge is reaching out to the masses. How to reach out to the masses? And there, for these two aspects, nowadays, Indian Geotechnical Society is focusing. So first of all, if you see, for the quality, we are trying to establish virtual universities in the same way as our Issmg body is developing. So we are trying to follow them. Then we are trying to do the accreditation of laboratory from the Indian Geotechnical Society side. So these are the some measures which we are taking to improve the quality. And as far as reaching out to masses are concerned, we are organizing several technical committee related Issmg conferences. And also we are trying to bring the, as I said, virtual university, professional engineer bill in parliament, etc. So these are the things where Indian Geotechnical Society is striving hard. With that, let me introduce to our first two speakers of this first session. First is the Professor Deepankar Choudhury. Professor Deepankar Choudhury is a chair professor and head of civil engineering department at IIT Bombay. He is well-known face and he is elected fellow of various prestigious organizations like NA, National Academy of Sciences, American Society of Civil Engineers, Institution of Engineers, Indian Geotechnical Society, Indian Society of Earthquake Technology, etc. He is Humboldt Fellow of Germany, JSPS Fellow of Japan, and TWAS VS Fellow of Italy. He is highly cited and he has more than 300 technical publications to his credit, and he has co-authored textbook on foundation system for high-rise structures and Issmg design guidelines on combined pile raft foundation. He is secretary of TC 207 and former secretary of TC 212 and member of TC 203. So our next speaker is Dr. J. Kumar Shukla. Dr. J. Kumar Shukla is presently leading the technical development strategy, geotechnical consulting assignments, and geotechnical instrument activities for the company Geodynamics. In 2007, he joined leading design consulting organization L&T as senior geotechnical engineers and has worked on several prestigious power projects. In fact, he has more than 20 years of experience in the field. He has obtained his PhD from IIT Bombay. He is also executive committee member of Indian Geotechnical Society presently, and he is actively involved in R&D activities and has more than 30 research publications to his credit. And he is a member of several board of studies in civil engineering and faculty board of engineering and technology of several universities. And he has guided several postgraduate dissertation, etc. So with that, from our side, our introduction ends. And I think Professor Luis, now Professor Di Mello, it's your turn now. Thanks.
Thank you very much, Professor Shahu. Thank you, our colleagues from India. Bom dia aos colegas brasileiros. It is a pleasure to be here hosting the session together with my colleague, Professor Shahu. We have heard interesting information about the broad challenges that our colleagues in India face. I think we are dealing with two continental size countries. In Brazil, other than the Himalayan problems that Professor Shahu mentioned and that we have heard yesterday, very interesting information with relation to challenges in bridge foundations associated to rock slope engineering. We also face interesting challenges. Our geology is a little bit quieter, let's say, on tectonic aspects than you in India have, especially in the Himalayan range of mountains. But we also face challenges from sedimentary quaternary deposits, highly compressible soft clay deposits, to weathered basalts, weathered granites, gneisses, soft sandstones, expensive sedimentary rocks, in different climates, from Amazonic region to the extreme south of Brazil to semi-arid environment as the Northeast coast. Challenges exist. And I think one of the most interesting aspects of our first day of webinar was that we raised a lot of attention. I want to share with our Indian colleagues that when their webinar finished yesterday, it was lunchtime in Brazil. And the Brazilian Society has a YouTube channel where webinars like ours are recorded and made available to all members of the Brazilian Society and external persons, free access. We have had more than 800 persons browsing, showing interest to check out what the webinar was about, which is an impressive number, showing to us that our goal is achieving. Following very interesting presentations from Indian colleagues and from Brazilian counterpart of yesterday, we today are going to focus on foundations and on soil improvement. The Brazilian Society chose renowned professionals and academicians to represent us in this interchange with the Indian colleagues. We're going to start by hearing two colleagues from the state of Rio de Janeiro. Professor Francisco Lopez has studied his underground studies and his master degree studies in universities in Rio de Janeiro, having gone to the Imperial College of the University of London for his doctoral research and degree. He teaches and researches in the Federal University of Rio, consults in important infrastructure and offshore structures, having written 2 textbooks on foundations, which are reference books throughout Brazil. And he has more than 100 peer-reviewed technical papers. He's going to be joined by a colleague, Professor Paulo Santamaria, who has also studied in Rio de Janeiro, having gone to Oxford, also in England, for his doctoral degree. Professor Santamaria has a very recognized consulting activity, as well as leads research in the Federal University of Rio de Janeiro, focusing mainly in foundations for important infrastructure and offshore structures. These 2 colleagues will be presenting the lecture on foundations. They are going to be followed by Professor Nilo Consoli on soil improvements. Professor Consoli has done his early studies in Brazil in the Federal University of the extreme south state of Brazil, Federal University of Rio Grande do Sul, followed by a master program in Rio de Janeiro and a degree in Concordia, Canada. He lectures at the Federal University of Rio Grande do Sul and is known for his high-quality research, being recognized worldwide as an international researcher. Very recently, last year, 2020, Professor Consoli was listed among the 2% most influential researchers in the world, according to a study developed by Stanford University. And this is an honor for Brazil to have such a colleague among us. Professor Consoli has more than 200 technical papers peer-reviewed, a book, and a very productive consulting career and assignments. I handle the floor now back to Professor Choudhury to open the session with the technical presentations. Professor Choudhury?
Yeah. I invite Professor Deepankar Choudhury now to present his technical presentation. And Dr. J. Kumar Shukla will also supplement after him. Thanks. Please go on.
Good morning to our Brazilian colleagues and good evening to our Indian colleagues. Namaskar. I hope the slides are visible. Is it visible, the slides, if anyone can confirm?
Yeah, it is visible.
Yes, Professor Choudhury.
Okay. So thanks to Professor Choudhury for your introduction, and nice to meet in this online platform again, Dr. Luis de Mello, after our meeting in Goa in 2018. And all our colleagues, friends, and students, members from both Brazilian society as well as Indian society, I hope you all are staying safe in this difficult time of pandemic worldwide. So let me directly go to today's presentation. So before we start, we already know about this geo-friendship between India and Brazil. And again, thanks to Dr. Luis, who came to IGS Goa event for the second Dr. Victor de Mello's Goa lecture. And thanks to Professor Purnanand Savaikar and his team, and Professor Babu, who was IGS president that time, who actually started this geo-friendship to come to a physical collaboration through this programs of conferences, events, and today we are meeting again for this webinar, and thanks to the present organizing team. Some collage, we can see that from the present organizing team, Professor Nilima was there in that event, and also yesterday's speaker, Dr. Chitra was there, and many other colleagues were there. So thanks to all of them, and thanks to Professor Savaikar and his team once again to start this Indo-Brazil Geo-Friendship in 2018. Coming to the presentation, today I will be speaking about something theoretical and practical aspects on foundation. There are several students or doctoral scholars who work on this area at IIT Bombay. Some of them I am showing over here, whose work I will try to touch upon in today's presentation. And there are various industry partners, those who actually helped us to implement our theoretical knowledge in actual field problems through their support for their projects for the industry interaction. So before we start the technical presentation, typical copyright matters for the online presentation, like the technical matters and pictures, what I will be presenting in this presentation is fully copyrighted. and to me and my research scholars of IIT Bombay or the stated collaborators and industry partners, unless specified otherwise. And copying the same either in electronic or printed format without proper citation will be subjected to International Copyright Act or related materials. And knowledge and its distribution is always free, but not copying. Coming to introduction of the topic, we all know about the foundation system, whether we call it industrial structures, whether we call it power plant facilities, tall buildings, fertilizer storage areas, oil refineries, everything. If failure occurs, it is essentially a national failure in terms of economy, and many other failures can happen. So more challenges, that analysis of such foundation system in earthquake prone area or seismic area is more challenging. And we can see in worldwide, there is an actually escalation of the height of the buildings or structures for which a robust foundation system is required. So that's why today I will try to focus on this combined pile raft foundation. As we know, when we talk about the theoretical aspects of foundation, we always say that either shallow or deep foundation. One of the shallow foundation is raft, another of the deep foundation is pile. But the composite nature of these two foundations, combinedly, we call it as combined pile raft foundation or CPRF. In the brief introduction, what we can say about CPRF, this combined or composite foundation, it reduces settlement through soil structure interaction, and it reduces differential settlement also and lateral deflection also. You can see the load sharing mechanism as shown in this picture. And if we want to classify what are the different types of this pile raft or CPRF foundation, typically they can be called either as pile enhanced raft or raft enhanced pile. This is essentially in the ICE London manual, the geotechnical manual, they're presented that how the distinguish between the pile enhanced raft or raft enhanced pile for the CPRF. There are several practical implementation of the CPRF. You can see that several structures in Germany and in Europe and Middle East, they are founded on pile raft, including Burj Khalifa. So this was probably the first structure which is founded on pile raft, and Poulos et al. In 2001, they described in detail about the pile raft concept for Burj Khalifa also, and this Messeturm Tower of Germany, which used a combined pile raft during 1998 to 1990. If you see the cost effectiveness, these are found to be very much cost effective compared to the conventional pile foundation. And you can see our publication of Katzenbach and Choudhury, which actually shows that for this Messeturm Tower, if it would have been using the conventional pile foundation, cost would have been close to $6 million more. So from this understanding, we actually brought out, the society actually brought out the Issmg TC212D foundations in 2013 Paris conference. This a design manual or the design guideline of Issmg based for the combined pile raft foundation, which you can see essentially depends on the theoretical aspect of 4 types of interactions: pile to soil, pile to pile, raft to soil, and pile to raft interactions, as you can see. So the total resistance of CPRF is essentially what the pile carries and the raft carries. And pile resistance, we know that is essentially the end bearing and the skin friction component, which are function of settlement, of course. And the raft resistance is also computed based on the stress generated below the raft is a function of the settlement, and the geometry of the raft, of course, as you know. So essentially what you see for combined pile raft foundation is mostly on the serviceability based design, where you decide that how much settlement you are going to allow for your structure, and accordingly you design. So all these details about CPRF and other types of deep foundations, including caisson, we have put it in this textbook, Foundation Systems for High-Rise Structures, published by CRC Press, with three of us as authors. You can find out all the details of combined pile raft under dynamic loading and all other details also. And this edited textbook on pile raft foundation by three of us, we actually brought it out in 2017 after the Taiwan event, and that also can be consulted for the detailed design and analysis for this study. Now coming to the specific focus on the capacity of CPRF, because people always want to know how much is the capacity or what is the bearing capacity. People, generally the structural engineers, they ask us, the geotechnical engineers, that tell us about the capacity of the foundation system. So this work is done by one of my former PhD student, Dr. Ashutosh Kumar. You can see the details available in Computers and Geotechnics Journal. The capacity of the CPRF he has actually estimated using the hyperbolic model of Lee et al. And proposed a solution. You can see this is the proposed expression, how to find out those interaction factors, alpha PR, pile to raft, raft to pile, and those things. And accordingly, how you actually estimate the CPRF capacity. You can see that the predicted results have been also validated through some of the centrifuge study results which were available. Coming further, the extension of the research work, the theoretical aspects I will be talking about. First, the dynamic loading aspects, are how the CPRF behaves under dynamic load. So my another current PhD scholar, Mr. Aniruddha Bhaduri, is working on this topic. And you can see our latest paper on this in 2021, this year itself, in Soil Dynamics and Earthquake Engineering, where he describes about how this dynamic loading on CPRF using the Pasternak-Scherbill model and the serviceability approach can be obtained. You can see this is essentially how the pile modeling is done. This is the governing differential equation, and this is the solution you can see using the triple Fourier function, and then the solution in the transform domain he has established using the inverse triple Fourier finally, and you can get the displacement functions, which actually, as I said, is the guiding factor for your design. So this is the solution in time domain when you try to do such rigorous dynamic analysis. Of course, the analytical method, this is the solution procedure which he has established. Further, one thing most of the time we geotechnical engineers ignore, or we try to simplify it, what we do, we generally consider the superstructure as a lump mass, and we consider that load is acting the vertical, horizontal, and moment at the foundation top level, and accordingly we design our foundation, whether it is pile raft, etc. But we actually, through this work, has shown that there is a significant influence of the superstructure, whether you consider it or not consider it. So this work actually was published in 2018 in Soil Dynamics and Earthquake Engineering, the work done by my previous master student, Yashodhara, and doctoral student, Dr. Ashutosh Kumar. You can see the mass spring modeling of the CPRF was idealized, and accordingly, the MDOF system has been actually used, and you can see that how this natural frequency of the system changes when you consider the superstructure. This is the dotted line, and when you don't consider or you neglect the superstructure. So this depends on the pile diameter also. So pile diameter plays an important role to identify on which frequency range actually you are going to operate or design. This is the amplification. As you know, we always try to avoid the amplification. So obviously, which frequency range you want to design your structure, considering the superstructure effect that is essential for such kind of foundation design. Now, all this theoretical knowledge or the theoretical development, what has been done, we have implemented it through various case studies or practical problems. I will just quickly give example. I don't think I have much time. These are the four projects I want to highlight where we have applied this kind of either large diameter pile or the pile raft system in various projects. So the first project of Vietnam for raw material storage unit, and this is actually supported by the ThyssenKrupp company. And this is the publication you can see where you get the data that details about the work that near the Ho Chi Minh City, 50 kilometers north of that, the site is located. And this is the raw storage unit or food storage unit. This is the retaining wall, and this is the raft and the pile, and that we have designed for them. And this is the size of the footprint of the raft area with 581 pile system. And here we have shown why we have gone for pile raft through our detailed design calculations, that only raft was not sufficient based on the soil condition, etc. And that's why CPRF was implemented. But obviously there was a choice directly to go to pile foundation, then cost could have been enhanced significantly. So that's why there was a cost saving as well as the safety measures in terms of the design or implementing the CPRF. You can see these are various design criteria like settlement, structural strength, and load bearing. And finally, we have shown that how the maximum settlement and the permissible rotation actually has been maintained for this project. Another project for Iraq, seismically active site. We did it for British Petroleum for the oil tank foundation design. And this is the site, Basra in Iraq. And this details you can find in this paper also, that IC Proceedings Geotechnical Engineering Journal in 2016. This is the soil conditions for that. And we have provided here 800 millimeter dia pile group of 89 numbers for each of the oil tank. And that finally has been constructed. And this is the client has sent us the picture later on. This is completed in the end of 2015 completely. This is another important project of nuclear power plant in India. This is the new nuclear power plant. The beauty of it is this is fully on the alluvial soil. There is no rock actually, and several agencies are involved or organizations are involved. IIT Bombay did the entire foundation rechecking and design. You can see both static and seismic conditions. So this is the location of that new nuclear power plant, which is coming up in Haryana state. And zone-wise, if you see, it is typically in the seismic zone map 2. So least vulnerable. And this is one of the iteration. This is the first iteration. Of course, for the sake of the confidentiality, we are not showing the final one. This is the first iteration of the problem which we have handled and solved at our place. Actually, Mr. Aniruddha Bhaduri and other researchers are involved in this work. You can see this is the reactor building and reactor auxiliary building. And this is the raft, irregular raft. And this is the number of piles, and piles are also of different length and diameter. You can see 1.2 meter dia and 1 meter dia pile, and length 36 meter and 30 meter are used at different location. This is, of course, as I said, this is in the first iteration. This is not the actual one which finally has been provided. It is the site construction of pile is going on now. That is the situation. The last example which I want to cite over here, the large diameter pile has been used for India's longest sea bridge project of MTHL in Mumbai, which is also almost close to the completion stage. This will be longest sea bridge of 21.8 kilometer length, connecting between two parts of Mumbai over this Arabian Creek Sea. You can see this is, as I said, total length of the bridge will be 21.8 kilometer and width will be 27 meter. Design period is 100+ years. It will be a 6-lane highway. And if you see, we have done both seismic analysis and static analysis of the foundation system, which L&T has actually given this project to us, and they wanted our advice. So we have done the dynamic soil structure interaction. Dr. Milind Patel was involved in this project, and we have used shake and finite element analysis for the site. This is the location, which is in zone 3, as you can see from the Mumbai's location. So pile length here, if you notice, the 36.5 meter of pile length with the diameter of 2.2 meter diameter were used. Also, piles were connected to 3.3 meter thick pile cap. So you can see the large size of this, which are nowadays very common, actually getting very common, which is for mega infrastructure project is very good. And you can see that pile cap supports 2 pier shafts of this much of length and pier head of 3 meters. So this is the pictorial representation. And after design, when the execution and construction was going on at different stages, both at the pile locations, after that pile cap and pier locations, we actually were fortunate. L&T invited us and we went and see. So this is the seismic analysis, what we did. And accordingly, the design was completed and given to them. So this is the actual picture from the site. You can see this is actually those 4 big piles, large dia pile, 2.2 meter. And on top of each of these 4 units of pile, 2 by 2, that pier cap, etc. came, pile cap came, then after that pier, and then pier cap, and finally the bridge will come. This actually will be a beautiful scenic view of this longest bridge of India, which is coming up, sea bridge, close to 22 kilometer. You can see the Elephanta Cave and other places. The Indians are very much aware about it. I invite our Brazilian colleagues, when things becomes again normal and we start traveling, please visit the site. You will love it, I can assure you. So these are this is the pile construction going on. And here, after pile, the pile cap is done. Now the pier construction. So at different location, at different pier locations, different things were going on, you can see. So in a summary, we can say that the evaluation of displacement, stress, resultant are highly important factors, which of course govern the response of foundation components. The connection rigidity in CPRF between the raft and pile should be chosen properly, so giving an allowable rotation in the raft, and that allowable rotation also is pre-decided by various design agencies or codes, international codes. Soil raft interaction dominates at the design at initial stage of loading, but at later stage, pile soil interaction plays an important role. And this peculiar behavior actually makes the CPRF to be more utilized in the actual design, depending on the tolerable lateral displacement, not only lateral, but vertical displacement also. So for the seismic design of CPRF, the condition of resonance must be checked. And what I have mentioned, that effect of superstructure, which many a times we ignore, the height of the superstructure, the stiffness coming from that, all those things must be taken into the foundation design aspect. So with this, I complete my presentation. Dhanyabad from India. Obrigado for my Brazilian friends, and thank you for all the international friends. So if you have any query, anything, comments, you can always put it, and I will probably now wait to see Dr. Jayakumar Shukla's presentation. Thank you so much.
Dipankar, we will be taking the queries at the end of the first 2 lectures.
Sure, thank you.
So please be with us till the end. So Dr. Shukla may now begin.
Professor Chaudhary, let me just, Professor Francisco Lopez, will you start your presentation?
I think the other speaker. Acha, okay, you want first one and then.
Yes. I am informed, Professor Chaudhary, that Professor Francisco Lopez will start, followed by Professor Paulo Santamaria. They are putting a joint presentation, starting by Professor Francisco Lopez.
Yeah, but this after Dipankar, this J. Shukla is there. His co-speaker, co-presenter. So Dipankar has.
So, I'm sorry. Okay, I'm sorry. The program that I have does not present Dr. Shukla. I'm sorry, Dr. Shukla.
Yeah, these two people are presenting combinedly.
I'm sorry, Professor Shukla.
Yeah. Professor Shukla, please go ahead. Please unmute yourself, Professor Shukla.
The screen is visible?
Yeah, screen is visible and your voice is also.
Okay.
Yeah, go ahead.
Good afternoon to everybody, Indian colleagues, and good morning to all Brazilian colleagues. I don't know whether, I'm not sure whether, yes, yeah, okay. So after the excellent presentation of Professor Deepankar Choudhury, I'm going to describe some of the recent developments as taken up in Indian infrastructure, as well as some of the upgradation in the field of geotechnical engineering and geotechnical instrumentation has happened. Some of the things I am going to describe over here as an augmentation to the foundation theory and practice in India. The contents will be developments in geotechnical investigations. So some upgradation has been happened. Then developments in large diameter pile foundations. So design and construction, some of the case studies which I have been extending what has been described by Professor Deepankar Choudhury. Then developments in foundation instrumentations and testings, and few monumental structures. So if we go with the conventional geotechnical investigations, be it in India or in some of the underdeveloped or underdeveloped countries, we usually do this soil investigation using conventional tripod rigs. And that tripod rigs may be sometimes augmented with some of the drilling machines, which has been more convenient for drilling into the rocks, what we call as a rock drilling machines. So if you say this would be let's say conventional tripod machines, this is augmented with some new diesel engines and the tripod machines which will be drilling into the ground. And if you see in the soft soils, these drillings are very conventional in India. This was the case up till now, but now there are few people or a few colleagues who has already brought new machines into India. And those machines are, let's say, imported machines, but can drill up to 70-80 meters and can drill into the rocks. It has the automated equipments fitted with it, along with the automatic SPTs as well. And if you see, looking to those particular rigs, some of our Indian engineers has developed their own rigs for better geotechnical investigations in the country. So now I think many of the Indian engineers have come up with a semi-automatic or automatic rigs for soil investigations, which can drill up to let's say 70-80 meters, not only drilling into the rocks, but taking samples from the soft soils and samples. Mostly these new rigs are fitted with automatic SPTs. So now usually the cathode and the drop hammers are not conventionally used. And nowadays you will see these sophisticated rigs all over working into the India and around it. Including into the marine conditions, you will see this kind of automated rigs or semi-automatic rigs have been employed. And we understand that using this kind of say better equipments, the geotechnical investigation is going to let's say see better sampling or better quality data and optimizing designs. So this would be another augmentation into Indian geotechnical industry to get a good sampling, good soil investigations. Again, as if you see, the soil investigation will be always largely depend on, in India specifically, depend on standard penetration test. And this standard penetration test, it has plenty of non-standard variables. And in India, people are using so many separately, or I would say homemade rigs for conducting the SPTs, and they have variations in hammers. So they use safety hammers or automatic or donut type of hammers. Mostly they have, let's say, operations by manual operations, and very few rigs has semi-automatic or automatic operations. Drill rods also has a variation in size and a length. Some people use a VX size, and some people use 3 meter long. Some people use 1.5 to 2 meter long drill rods. So there is no standard into the drill rods and the rod size. But at the same time, if you see the lifting mechanism also has a plenty of variation. So cathode or rope type of lifting mechanism, or let's say spooling winch, or nowadays recently it has been improved into the chain driven kind of arrangements. And drilling methods will be hollow steam augers. Very few rigs has these attachments of conducting with hollow steam augers, and mostly in India it is drilling through fluids only, and people uses bentonite or a locally available clay material as a drilling fluid. And split spoon sampler, the shape and the size, they are with or without liners. So there is plenty of variations and plenty of non-standard things practiced in India. But if you see, to mitigate these things, recently the fraternity has introduced, or let's say started aligning towards the SPT energy measurement for each and every rigs. So what it means is conducting a SPT, and you attach instrumented SPT rods into the rigs, and then those rigs, this instrumented rod will be connected with the accelerometers, and these accelerometers will be then connected with a PDA device, or I would say pile driving analyzer, or you may have separate SPT analyzer from pile dynamics, to understand what would be the energy transfer into the borehole or through your rod, so that you will be able to understand your SPT penetration, SPT values, how much reliable those SPT values. And in most of the cases, these energy measurements have been conducted considering ASTM D4633 or ISO 22476 part 3 as a reference. And if you see, this would give you a clear, let's say, arrangements that the rig is fitted with the, let's say, instrumented rod. If you can see, instrumented rods are there. And these instrumented rods are then connected with the PDA machines. And when you take the blows, it and measures the energy. And if on your screen, you can see over here, that is energy transfer ratio, which is called ETR. And that particular is as an indicator of actual energy transferring into the SPT rod or a rod, which is connected with the split phone sampler. And this 70% means the theoretical SPT energy. So what your 65 kg hammer is, let's say, dropped from a standard height of 760 height. And then if you consider a theoretical energy against the measured energy of energy transfer, then this means that your say 75 or 76% energy has been transferred onto your energy rods. Now, this cannot be considered for a single, or I would say one blow. Probably you need to do with the plenty of blows to understand the variations and the average. And you also need to do with the, let's say, variation in the depth. So similar exercise has been conducted, and if you see over here, there are total 37 blows are there, and on energy transfer would be approximately 77 to let's say 76. And if this is the theoretical energy measured, and this is the ratio of theoretical energy, let's say imparted. And if we go with the depth, let's say if we say measured at a depth of a beginning depth of 34 meter, 35 meter, and 36 meters, the measured SPT energy transfer is 77%, 75%, and 78%. So this is a pretty good average for any of the semi-automatic devices, which is presently conducting plenty of investigation in India. However, there are other rigs also available. So we try to compare some of the rigs and their performances employed in the same project, so that we can understand that if any one rig is giving SPT energy penetration resistance, will be comparable to some another rig, or say the investigation carried out by another rig. So if you consider this is a rig number 1, and the SPT has been conducted at a 3 meter, 5 meter, and 6 meter depth, the average energy ratio is 73, 75, and 79. So if you consider all the average of 3, that would gives you 76%. We usually consider N60, so which we consider as a standard 60% of energy transfer. So if somebody is going to evaluate a liquefaction potential or some another analysis, then they need to further scale up the SPT blow counts to get them SPT N60, or then they can do some corrections for N160 to make it comparable with international standards and correlations. If we go with, let's say this is one semi-automatic rigs, which has overall satisfactory performance. Then second one is, let's say conventional RD30 with tripod rigs. And if you go with the beginning depth of 12 meter, 13.5 meter, and 15 meters, the blow count, or say the energy transfer, is 80%, 74%, and 73%. If you go an average of it, the average is 76%. So this particular rig, even with the, let's say, Dunette hammer or a cathode type of hammer, gives you considerably good SPT energy transfer. And however, what thing is not can be managed over here is the blows per minute. That means there are some standard recommendations for liquefaction potentials, and as per, let's say, Indian standard 2131, that the SPT must have blows per count, or say blows per minute, in the range of 20 to 30. Some also uses 20 to 40. So if you, but with this kind of arrangement, you cannot achieve SPT blow counts, which has been theoretically described in the standards. So you need to have some automated energy, or say automated rigs to work on energy, or say SPT blows per minute. This is another endogenously developed.
Dr.
Yes, yes.
Kumar, I would appreciate if you
We quickly,
because
we
we are running short of time.
Okay. So that's okay. So takeaway is we are improving into geotechnical investigations, and we are expecting some more better quality data. This is another one. In India, usually the bridge foundations have been constructed using well foundations. So nowadays, as Professor Dipankar has already described, the large diameter is the way forward. So I will be discussing on package 2 of the same package. He has described on package 1. So it is Mumbai Trans-Harbour Link package. Going quickly, the package 2 is costing around almost approximately 3,800 crores, or what we can say in Indian rupees. And the project details are already there on your screen. The soil investigation has been carried out in number of boreholes, so 154 boreholes in marine. Intertidal zone, it was 18 boreholes, and the land and interchange 132. Mostly it was let's say subsoil in the top, marine clay, followed by the granular material, and then followed by the highly weathered rock to moderately weathered rock. The rock is mostly a basalt or basaltic formations. So statistical averages has been taken out for conducting the design soil profile. And then this was the configuration of a pile for 2 meter diameter pile, which is let's say loading up to 20 meganewton, or we can say 2000 ton per pile. The loading has been applied, or say design load has been there. And the configuration is on your screen on this. They are in the, let's say 4 numbers of 2 meter diameter pile. And if you go with the, let's say another configuration where the 3 meter diameter pile was used, the loading on the per pile was approximately 28 meganewton. And the construction was carried out using reverse circulation drilling, and that has given a considerable productivity, and project was expedited because of faster construction and faster drilling into the rock using reverse circulation drilling. If you see the construction arrangements, the reverse circulation drilling rig is over here. Then the pile jacketing, or say the pile has been, main pile is over here, and the platform has been supported on jack-up barge. The muck which is extracting out of it, it will be filled into a barge which is close to the crane. And then you can have a casting, concreting, the separate barge supported batching plants have been there, which will be pouring the concrete into the piles. So this kind of arrangement has been done for each and every pier. This was the profile. Now the major was that how to test them and how to ensure the capacity of pile. So the bidirectional static load testing was employed, and geodynamics has carried out a first cut predictions of putting the load cells at 17 meters. And if you lower it down to 19 meters, this would be the response. It was the final load test was compared with the simulations, and it was quite good matching has been achieved. And you can see that both the upper part and the lower part, bottom plate and down plate has been almost matching with the predicted behavior of pile. And if you see the conventional top-down load curves, if you develop from the bidirectional static load test has been performed, then it is matching with the simulations, and the capacity of pile has been derived that it was much more, pile has a possessing much more capacity than the design load. This was some of the photographs, and if you see on this was the design, let's say parameter which was assumed for the pile configurations, and this was the mobilized shaft resistance for the based on the strain gauge and foundation instrumentation. And you can see the I would say bidirectional static load cells installed with the reinforcement cage. The another project was Mumbai Coastal Road project, where the similar pile has been tested. 2 meter diameter piles, the bidirectional static load cells have been on your screen. Recently we carried out a 3 meter diameter pile, and the pile was loaded up to 10,300 metric ton, or you can say 103 meganewton. And they have been also conducted, the load testing has been conducted in the marine offshore conditions. Then the confirmatory load testing for production piles will be by high strain dynamic load testing, and the hammer weight was approximately ranging from 17 ton to almost 24 ton. So these are some of the summary of the load testing conducted at site. If you really would like to know the load transfer at the tip, or I would say end bearing resistance, then we conducted one particular test installing the tip load cell at the base, and this tip load cell can directly measure the load transfer at the base. And if you see, these are the photographs of actual construction happening at site at one of the power project sites. Then Mumbai, another let's say major infrastructure project which is currently going on is Mumbai-Ahmedabad high-speed rail corridor, what we can say a bullet train project. And if this bullet train project, the costing is approximately in terms of 1 lakh crore, and it has been divided into many of the packages. So presently the construction has been starting from Ahmedabad to Vapi region. This is in the Gujarat region. The construction is already going on, and this is probably going to complete in the December 2024. And the elevated viaduct was adapted for this to save the land, because the land acquisition is one of the issue in India. However, this particular entire project of approximately let's say 400 to 500 kilometers will be on elevated corridors. The Statue of Unity, this is well known to everybody, but recently our engineers have started doing some of the let's say unconventional designs for a statue. So this is one of statue of Lord Shiva, and our other colleagues, Dr. Abhay Gupta and Ravi Sundaram, has been instrumental in design of foundations of these unconventional structures. Because of wind and let's say the geometry and the CG, the raft of this particular structure was designed using rock anchors and irregular shape. So that was the challenge, and raft was augmented with 8 to 10 meters of rock anchors, 100 mm dia ground anchors, which was grouted with GP2 non-shrink grouts. You can see the red points, those are the anchor locations where anchors have been installed. And this is some details that the owner is Mirage Group of Industry. And on your left hand side, you will see the under construction of this Lord Shiva. The structure has been already erected, and if any Brazilian friends are visiting India, they can visit this particular place, which is a beautiful one. Thank you. I think I have been still in the time.
Yeah, thank you, Dr. J. Sukla. And now I request my counterpart from Brazil, Professor Luis de Mello, to take over. You are muted, Dr. Luis. You are muted, Professor Luis. Muted. Please
okay. Yeah. Yes, thank you, Professor Shahu. Thank you, Professor Choudhury and Professor for your very interesting presentations. Let's go on, and I call Professor Francisco Lopez from the Federal University of Rio de Janeiro to take over the floor and deliver his lecture.
Hello, good morning to my colleagues in Brazil. Good evening to my colleagues in India. I'll share my screen with you. The presentation is entitled Static Load Tests on Piles, Methods, Interpretation, and Use in the Quality Control of a Piling Work. The presentation was prepared with my colleague, Paulo Santamaria. Part 1, I'll be describing test methods and interpretation, the Brazilian practice. Part 2 will be presented by Santamaria. Now, test methods. We have the conventional or top loading method, in which a jack is placed on the top of the pile and loads the pile reacting against a reaction system, which may be a cartilage, beams connecting to nearby traction piles, or a set of anchors. Typical instrumentation is a load cell and displacement gauges at the pile top. We also have the O-cell test method, also called Bi-Directional Method. It was first proposed by the Brazilian engineer Pedro Elísio Silva in 1983 and was independently proposed a couple of years later by the American Osterberg. In this test, fluid is pumped into an expansion cell placed somewhere along the pile shaft, close to the pile base. The cell expands and loads the lower section of the pile downwards and the upper section upwards, so there is no need for a reaction system. Here we see on the left a medium-sized diameter pile with one expansion cell being lowered into the borehole, and on the right, a large diameter pile with 3 expansion cells already installed. The typical instrumentation is a set of displacement gauges resting on the pile top or on telltales, which are connected to the cell top and bottom. Now, loading modes. The more common is the incremental load mode. On the right, we see a quick incremental maintain load test in which the load increments are kept for a short period of time, such as 15 minutes, and the settlements do not stabilize in this time. On the left, we see the more common incremental maintain load test with longer time of stabilization until settlements come to full stabilization or very close. The British have also the rate of penetration test shown on the bottom of the page, not used in Brazil. The difference between a slow or a stabilized load test and a quick or non-stabilized test is that the quick load response is stiffer and indicates a higher bearing capacity. So if we load in stages and we want to reach a stabilized curve, we have 2 options. Suppose we are on point A, which is the end of a stage, and we want to reach the stabilized curve, which is the dashed line. We can go from A to B, which means under constant load, or we can go from A to C, which is allowing the load to relax. Time to reach point B is much longer than to reach point C. So this is the idea behind the equilibrium method proposed by the Indian authors, Mohan and others, in 1967. So in the equilibrium method, we have the load kept constant for a short period of time, such as 15 minutes, and then allowed to relax. And in the end of the relaxation time, we come to a load in equilibrium with the displacement, which is indicated here as Q2 and W2. This pair of values are taken to the load settlement plot, and we get this solid line indicating the stabilized load settlement curve. The equilibrium method has not been included in the Brazilian standard yet, although we have had some discussion. Some tests have been carried out, mainly in research, such as on a model pile, soft clay in Rio de Janeiro. The pile was first loaded in the quick loading mode and indicated a failure around 7 kilonewtons. Then it was unloaded and reloaded in the equilibrium method a couple of times, indicating the bearing capacity somewhere between 5 and 6 kilonewtons. Now, interpretation of the load settlement curves. If we have results of a conventional top loading method, we can apply one of the various criteria to define the bearing capacity, because very often the load settlement curve does not indicate a clear failure. The Brazilian Foundation's standard prescribes that we draw a first line corresponding to the elastic shortening of the pile. There's a freestanding column and a second line parallel from a distance of pile diameter divided by 30. So at the point this second line meets the load settlement curve, we get the bearing capacity of the pile. Now, if we have run a bi-directional test, the interpretation should lead to what is called the equivalent conventional test curve. Because from the bidirectional test, we get a pair of curves, one indicating the behavior of the lower section and the other of the upper section. And what we want is a load settlement curve that describes pile behavior when loaded from the top. So there are a couple of proposals. One, the original Silva-Osterberg proposal, in which we select a displacement and get two loads from the two curves, and we take to a graph where this displacement is plotted against the sum of the two loads. The Cruz procedure is somewhat different. You select a load stage and take the two settlements or the two displacements and take to a graph with the average displacement and 2Q. The advantage of the Cruz procedure is that you can build the load settlement curve as the test progresses. You don't have to wait for the end of the test. There are a few comparisons between results of the conventional test and the equivalent curve. Most of these results come from the two types of tests being performed on the same pile. First by the bidirectional method, and then after the cell is grouted by the conventional method. But results are close despite the fact that the second test is affected by residual stresses from the first test. There are a few results from Brazil, but what quite often happens is that in the bidirectional method, one of the pile segments fails first. In this case, the lower segment has failed before the upper segment. And if we do an extrapolation of the failure load for the upper section, the result will not be so good. So let's do something else. Let's do an exercise which is to construct both test curves for a hypothetical pile. Suppose a static load test on a 0.40 meter diameter concrete pile, 11 meter long, in a homogeneous soil. The soil has a shear modulus of 18 megapascal, Poisson's ratio of 0.4, and the pile develops a unit side friction of 50 kilopascal and a unit tip resistance of 3,500 kilopascal. Let's first assume it is rigid. The load settlement curve for this pile, loaded from the top, can be constructed with two data. The first is the bearing capacity. We work out, given the unit side friction and unit tip resistance, we have a bearing capacity of 1,130 kilonewtons. Now the settlement for the working load, supposing a rigid pile, we can get from Randolph's solution, shown here the equation. So if we input the working load, which is 1/2 of the bearing capacity, we get a settlement of 1.83 millimeters. A complete load settlement curve can be obtained with a mathematical function, considering these two results, for instance, using van der Waals equation. This is van der Waals equation, known the ultimate bearing capacity, the working load, and the settlement under the working load. We can work out the parameter alpha as 0.379 millimeters to -1. Now, this is the load settlement curve constructed for this test. The curve has as asymptote the bearing capacity of 1,130 kilonewtons and passes along a point which corresponds to the working load and the working load settlement. Now let's suppose that we have decided to carry out a bi-directional test on this pile. The ideal location of the cell would be at 2 meters from the tip. So we have a 9 meters segment and another one 2 meter long. One is loaded from the bottom and the other one from the top. Now the upper segment, we will construct the load settlement curve with the bearing capacity of 565 kilonewtons. The upward displacement can be obtained with Randolph solutions for a rigid pile with load only from the shaft, and we get 1.11 millimeters. The complete load settlement curve, according to van der Waals, will have a parameter alpha 0.626 millimeters to the -1. And the lowest segment of the pile, we do the same. We have the bearing capacity, the settlement and the working load, we have the alpha parameter. So we can construct the pair of curves that would be produced by the bi-directional method. The upper segment curve is stiffer, as would be expected. Now, if we build the equivalent curve by Silva-Osterberg proposal or by Cruz, we have a good match with the conventional test curve. Now, if we use a different proposal that takes into account the elastic shortening of the pile, we get more settlement, a different curve. So the conclusions are, for a rigid pile, both procedures, Silva or Cruz, conducted the same and apparently correct equivalent curve. Now, if the elastic shortening of the pile is considered, the resulting equivalent curve is different, indicating greater settlement. So the elastic shortening can be either measured by displacement indicators or computed as suggested by Massad. Therefore, it's important to take the elastic shortening into account. Now, final remarks on the bidirectional method is that it has as advantage less cost and time, as the reaction system is not needed. Shortcomings, it needs careful selection of the cell depth. If the cell is not placed at the right depth, results will be not so good. And it's best suited for cast in situ concrete piles. So I thank Felipe Cruz, Leandro Soares, and Bernadette Danziger, and now part 2 by Paulo Santamaria. Thank you.
Professor Santamaria? Professor Santamaria, are you
hello.
joining us and uploading your lecture?
Now, is there any other person who will also be presenting? Yes.
Yeah. Yes, Professor Paulo Santamaria is now on the screen. He is uploading his presentation.
Yeah, please, go ahead.
Okay. I was having a problem with the sound. So can you hear me now?
Yes, Paulo.
Okay. Share the screen. Well, okay. Thank you, Francisco. Thank you, Luis Guilherme. Good morning and good evening to all colleagues from Brazil and from India. My presentation refers to interpretation of load tests performed as a means of verifying the safety of piling work. And, this can only be accomplished reliably using probabilistic methods. Also, I must say that I am quite aware that not everyone is familiar with these methods. So while some equations related to probability will appear, my emphasis will be to draw special attention to the concept and the most relevant aspect of this subject. So let's get started. The agenda is we start with introduction, then we talk a bit about the Bayesian updating, then updating pile capacity load tests, then an alternative approximate procedure, reliability of piles, and finally quality control of piling work. Uncertainties in pile foundation design. Where do uncertainties come from? As far as geotechnical parameters are concerned, measurement errors, spatial variability, and across a site and a small number of samples. Concerning analytical numerical models, simplification of a complex physical reality. And finally, with respect to construction processes, I can say that they vary from pile to pile. So how to deal with these uncertainties? Either perform load tests on a small number of pile samples or adopting conservative factor of safety. Depending on the size of the pile work, either option A or option B can be chosen. So according to the Brazilian Foundation Code, load and tests are mandatory for the following cases. So for segmental hollow auger, whenever you have more than 50 piles, or bored piles, diameter larger than 70 centimeters, root piles, micro piles, whenever you have more than 75 piles, and all other piles whenever you have more than 100 piles. Let's talk now about Bayesian updating. Reverend Thomas Bayes' miraculous rule. That's the point. And let's say a little bit of history. Bayes lived in the 18th century, and his work was published posthumously, becoming subsequently enormously influential. So the message is Bayes' work is an outstanding and powerful tool for, in our case, for engineers. That is because it's a way of capturing uncertainty caused not by randomness, but by simple lack of knowledge. I'd like to repeat this, caused not by randomness, but by simple lack of knowledge, which is epistemic uncertainty. And therefore, one can always reduce it by using evidence. In plain words, Bayes' theorem shows how the chances of our belief in a specific claim or theory should be changed in the light of fresh evidence. Bayes' theorem shows that we can update our initial, we call prior, level of belief or knowledge in light of new evidence by multiplying by a factor known as likelihood function. So new level of belief equals old level of belief plus weight of new evidence. Let's see a bit of graphic illustration. If in a universe you have an event A and an event B in this Venn diagram, the intersection is right here, showed here, and the probability of that intersection occurring is a probability of A given B times probability of B, or probability of B given A times probability of A. So using this equation, we can derive the second equation, which is basically Bayes' theorem. So the meaning of this is the posterior probability. This probability of A, B given A is likelihood. Probability of A is prior knowledge, and probability of B is the evidence. What actually happens usually? due time and budget constraints, and also limited site investigations and tests, design performed by simple methods, usually SPT, etc. This gives us the prior knowledge, and using Bayes theorems and also pilot test during construction, adding this knowledge to the prior knowledge, we can get the posterior knowledge. In summary, the more information added to a pilot design, the less uncertainty or entropy, which is the same, associated with that design. There is a problem, which is the prior probability issue. This is what happens sometimes there is no prior factor information. I would say that in technical engineering, soil geotechnical engineering, file engineering, this is not quite usual. Usually you have some prior factor information, but if you don't, an uniform prior distribution may be assumed. And this uniform is called also diffuse prior or uninformative prior distribution, which is a rectangular distribution, like in this diagram here, with a constant density of probability over the range A to B. That represents the principle of insufficient reason or principle of indifference. Engineering experience and judgment, which are subjective information, can be incorporated in prior distribution. This is a very important question. So, updating pilot capacity load tests. Let's then examine the three cases that happen in practice. First case, proof load test that pass. According to Brazilian Foundation Code, we have the design based on analytical method, allowed the spread design, and verified by proof tests. Maybe not mandatory, depending on quantity and working load, as I have said. So the design load is the predicted pilot capacity divided by a factor of safety. Then we have this, this scenario over here. So the minimum test load is twice the design load. And this diagram represents this. Our test, proof test starts here and stops here, right on the twice the design load. So this is this known region. This is the unknown region. So we do not know the ultimate load, ultimate bearing capacity. But you can use Bayes anyway and get in this expression. Let's tell you what this means. This is the posterior function, f double dash of me, where me is the mean of the pilot capacity, the mean value of pilot capacity. F is the distribution, is equal K, which is normalizing constant. L of me is the likelihood function, and F dash me is the prior function. Before we go to the second case, I must tell you that from this procedure, we can obviously get update pilot capacity, but it's not a straightforward calculation. It's a bit difficult. In the second case, proof load tests that do not pass, or N tests, we have R tests that pass. So R is the load is maximum load is twice the design load, as represented on the left diagram here. No, yeah, no, that one is the on the right diagram here. So we have this, like the first case, R maximum load is twice the design load right here. So it's similar to the first case. And N minus R will have the ultimate load lower than twice the design load, represent on the left diagram here. And repeating this diagram again for illustration, you have base again, but in this case, this is the function, actually the function the same. What changes in here is the likelihood function, which now is a binomial distribution because of the number of tests that pass and number of tests that do not pass. Also, as the previous case, this one is not straightforward calculation too. And the third case, load test conducted to failure. Well, this is not usual actually in Brazil. It can be done for research or reduce prior information for design, although this is quite expensive way of providing prior information. Anyway, in this case, you have the ultimate load. The distribution of pile capacity usually follows a log normal distribution, and this log normal can be conveniently converted to normal distribution to a logarithm. There is a recipe for this. We define the variable x, which is measured pile capacity divided by predict pile capacity. This has a log normal distribution. Then the variable y is the transformer, logarithm transformer, which has a normal distribution. A particular design method gives the empirical distribution, something like a SPT method or something else. And from known distribution in this transformed, you can get the prior function, prior distribution function, which is this. And the parameters are also stated here in these equations. And now, based on Bayesian sampling theory, we get the posterior distribution function f double dash of the mean value of bearing capacity. This is important. This is the mean value of the bearing capacity. So the parameters are stated in this equation. Is you have the mean value and the standard deviation, and y bar is the mean of load test results, y1, y2, y3, etc. Sigma is the standard deviation at the mid node, and the mean value and standard deviation of the population, rather than variable associated to the mean value, as I said before, can be obtained using this expression. So we have the parameters for the variable associated to the mean value, or can use the parameter associated to the single pi with the expression down here. Now, we are proposing actually an approximate procedure taking into account that the third case is the easiest to to derive as far as calculation is concerned. And on the other hand, let's assume that we don't have test conduct to failure. We have test conduct to twice the design load. What do we do? So one procedure would be extrapolate the curve, the load versus displacement curve, which stops right in here. We can extrapolate this curve for some extrapolation function. And from this, we can obtain this value RU, this ultimate value. Actually, it's not a value. This is a random variable in this case, because you have variability in this extrapolation. So we have a mean value and the standard deviation of this random variable. So first load test, second load test, etc. And now instead of having values, load tests, you have random variables of the load tests with a mean value of the whole set and a variance or standard deviation of the whole set. With this procedure, the variability of the extrapolation is taken into account. That's why we are using the simplest method and this load test up to twice the design load. And this produce a useful result. Beware, because the variability of the extrapolation function has not been considered. I mean, this is valid for one function, but there are many extrapolation functions possible. And this many extrapolation function will produce an additional variability that was not considered in this procedure. So having this, all we have to do is apply the methodology of the third case. Let's talk a bit about reliability of piles. If Q is the random variable concerning loading and R the random variable concerning resistance, we have this in this diagram here, the distribution of the loading and distribution of the resistance. So the reliability index, as you may know, is defined by this equation here. So with these parameters, the mean values and the standard deviation of both, we can get the bit value or reliability index. This equation is valid only for normal distribution, but we can also, beta can also be defined for the distribution function. Can use in some case analytical methods or graphical methods. According to Zhang, 2004, target reliability index beta S for single pile should be in the range from 3 to 3.5. And owing to group effects, pile group effects induced by overlapping stress in soils and other causes, and also system effects, interaction between group of pile and superstructure, reliability of pile group can be significantly higher than that of the single piles. This is what you know. And the target reliability index beta G for pile group should range between 2 and 3, also according to Zhang. Quality control of piling work could be sketched in this way. based on the proof load tests, as previously mentioned on the first case. So we have test load equals twice the design load. So we have the proof load tests. Do they pass or not? Yes, allowable stress design. Okay, so the piling works okay. No, now we have to start a Bayesian update procedure, and then with reliability analysis, you determine beta, and so is beta within the target? Yes, okay. No, review the design, reducing the pile design. Okay, thank you very much for your attention. And now I pass back to Professor Vitor de Mello.
Thank you, Paulo. Professor Chaudhary, I think we can now open the discussion sessions. Will you handle some questions from our Indian colleagues, and I'll handle some questions from the Brazilian group?
Sure. So the first question is to Jay Kumar Shukla. Are you there, Jay Kumar?
Yes, sir, I'm here.
Okay. So where was SPT energy measurements calibrated? This is Venu to Jay Kumar.
Yeah, I think we have been working into this energy calibration from 2015. So there are plenty of projects on which we have calibrated this. And more than 50 rigs have been calibrated or say measured for their energy transfer for this.
Okay, so calibration was done in-house, I suppose.
In-house in the sense, these calibrations, I would say the SPT rod is purchased through PDA. So energy calibrations or the rod calibration is done by PDA USA, File Dynamics India. But we are measuring the energy transfer. And that way we can say that we are calibrating the rigs to find out what actually energy transfer occurred during the soil investigation.
So second question is also related with this only. Hiran from Burma Geotech Consultant is asking how this SPT energy analyzer by Pile Dynamics is related to weight, length, and dia correction.
Yeah, actually, there are standard corrections for weight of the, let's say, the hammer, then the diameter of the rod you use for soil investigations, and the borehole diameter as well. But these are for standard penetration testing. This particular measurement is while you drop a hammer, or I would say whatever the standard hammer, whatever the country you work in, they have a standard height and a weight of the hammer. So this particular measurement shows you that against the theoretical energy which you need to be imparted on the top of the SPT rod, or I would say the rod which is connected with the split full sampler, gives you how much energy at the head of the rod. And if this energy is lower, definitely your SPT blow counts will be very high. And if your SPT, this energy transfer is high, probably your SPT blow counts for the same soil, same depth would be a lower one. And for all engineering correlations and designs, we usually require N60, which is the blow counts corresponding to 60% of energy transfer. So if we know this energy actually, then probably either we can scale it up or scale it down, the blow counts for considering into the design. So and as I said, the case was to demonstrate that rig by rig, this energy transfer differs. So on a same project, if these 3 rigs are working, the blow counts, if you don't know the energy measurements, then these blow counts are not comparable. And you probably will be grossly wrong in your design.
Okay, thank you. And so there are few questions to Dipankar. Professor, please, can I take up this Dipankar's question and then you can take the question from Raj?
Professor Shahu, don't you think that I have some questions from the Brazilian colleagues to Dr. Shukla? Do you think that we should keep a flow with him and then we address the other lectures? Okay.
Agree.
So, Dr. Shukla, there is a Brazilian colleague interested in knowing if there are Indian standards enforcing energy measurement in the dynamic penetration tests for routine, for normal engineering practice.
Actually, IGS is presently, Indian Geotechnical Society is now, let's say, actively working with the BIS, Bureau of Indian Standard, to get this particular inducted into the Indian standard. So presently it is not there, but let's say in a recent future, you will be looking into it, that code has been updated for these energy measurements. We IGS, under the umbrella and leadership of Professor Samadhya and Professor Sahu, we are working hard to get them inducted into Indian standard, because this is required for, let's say, harmonization of a design practice.
Okay, thank you very much. Another question to you is that if in India, the normal practice incorporates other investigation methods, for instance, the use of cone penetration tests, the Marchetti dilatometer, pressure meter tests, seismic downhole tests, if they are part of an investigation campaign for important foundation works or infrastructure works like roads and other embankments. And to that, I would link, if you have some comments to produce, to share with us for undisturbed residual soils practice in India, as well as for undisturbed quaternary deposits, either soft clays and or sands on Indian practice.
Yes, definitely. We have in Indian standard, we do practice with the cone penetration test, dilatometer test, and let's say pressure meter test. They will be, or say usually they are part of a let's say big geotechnical investigation program for any of the renowned project. However, what happened with this cone penetration testing is we usually end up with a refusal at a shallower depth because of limitation of the equipment. And usually in India, most of the geotechnical investigation agencies has a mechanical cone. However, we have recently, let's say, a few of the agencies, like our IGS colleague, Dr. Parth Sarthi and other people, they brought electronic cone, which are more, let's say, convenient or practicing for marine and offshore investigations. Because when you measure the pore water pressure, also along with the penetration, probably you have a better informed profile, and you can characterize the ground for even, let's say, for a piling and other jobs. But yes, dilatometers, pressure meters, they are also part of Indian standards, and they are usually part of a comprehensive geotechnical investigation program.
Thank you. Yeah. I hand it back to you, Professor Shahu.
Yeah. So now, may I request Professor Dipankar to answer a few questions?
Yeah, please.
Yeah, thank you. So there are 5-6 questions to you from our side. One is, can you suggest any alternative methods other than pressure meter test to find stiffness of soil with reference?
For pressure meter, other than pressure meter?
Yes. To find stiffness.
The E value.
Yeah.
Yeah, through correlations, we find out from other tests, as we know, because from SPT correlations also stiffness can be found out, but direct method, generally pressure meter test is recommended. Like for NPCIL project, we have used from pressure meter test. I think who asked that question refers to NPCIL project or something.
It
If
is
it is
Karthik.
NPCIL project, I can mention it is from pressure meter test. It was taken.
Okay, it is Karthik who was asking. Another
Achha.
question is, could you explain the difference between pile cap and pile raft?
Okay, good question actually. So yeah, many a times some people feel that probably pile cap acts as a pile raft, but it is not so, not at all actually. So pile raft is completely different than conventional group pile with pile cap. So complete design methodology, procedure, load sharing, behavior, everything is completely different for a combined pile raft vis-a-vis pile group with pile raft. So it should not be mixed or should be considered same. Yeah.
Okay, this is Anant Raj to you. First question is, if we take total superstructure effect on design of CPRF, combined pile raft foundation, then how the loading and soil structure interactions vary in pile cap compared to conventional design?
Yes. So here again, I think he's asking specifically for the pile group, because as he mentioned pile cap, I understand that he's referring to that. But in our analysis, we essentially took care of the pile rafts for CPRF. But of course, see, any analysis when we do, or the design when we do, we simplify it. So that is the reason why entire superstructure we take as a concentrated load, vertical, horizontal, and moment for design purpose. But if we take the stiffness of the superstructure, like various floor height and etc., which are required nowadays for important project and big mega project, you will see that there is a minute changes in the what is called your pile design also. The reason being what I briefly mentioned, because mainly for such tall buildings or structures where height is essential to produce some kind of stiffness from coming from superstructure, that influence in your seismic design also. And that changes based on your pile diameter, soil profile, everything, as I tried to show in some of the literature and our papers also one can refer. So in a nutshell, what I can say, yes, it is always good to use the superstructure effect for important design rather than ignoring it and just taking it as a concentrated load. So that's why you will see that our nuclear power plant project, which is very important one, they are along with the superstructure, the reactor building altogether with foundation has been analyzed. It is not that only all the loads of superstructure considered as foundation level and then the design of the foundation has been made. No, that cannot be done. So in a nutshell, that is the answer. Yeah.
So which software is more reliable to combine superstructure and foundation system analysis?
My answer probably will be not a single software. I will believe on the fundamentals and basic, because software can give you any type of result. Even if somebody claims that my software are 100% correct or gives the 100% result, I probably will not agree, because it all depends on how you give the input parameters, how you understand the problem, and accordingly you judge the output. Otherwise, it will be like a non-engineer's work. Anybody, any school kids also can input some parameter and get the result. If software would have been so robust, of course, software is robust. It has inherent capability of having like numerical problems to solve. But what I want to emphasize is, I probably will not name any software which is as of its own 100% can stand alone without having the knowledge of the human being who is actually handling that software. That is the comment I will like to make.
So we have got some more comments, but I will stop at that and request, because we are running short of time. So I request Professor Luis to take up some comment from Brazilian side.
Okay.
Okay, I'll do it as quickly as I can also, Professor Shahu. I have a question for Professor Lopez as well as for Dr. Shukla. Do you have any thoughts or considerations to share related to use of OCells with relation to effects of residual stresses linked to installation as well as to the cure of concrete on affecting the results or the information gathered by OCells, by the Osterberg cells? Francisco, go ahead first and then Dr. Shukla.
Yeah. I think you touched one of the R&D topic. What we have observed is while installation of strain gauges, and if you monitor the strain gauges before installations and after installations, due to curing as well as the residual stresses, probably you will get back some echoes of the stress which has been logged inherently during casting. And if we really analyze them, then probably we will get back or say get some particular trend on it. We have plenty of load tests carried out, so results are already with us, but we have never analyzed them for these residual stresses. But yes, the strain gauges are direct measurements of all these residual stresses. However, for the rock, the piles which are installed into the rock, we don't see that much of residual stresses. But for the load test, which has been conducted into the, let's say, deposits, or I would say the alluvial deposits, and due to drilling methods which we are implementing, we have some particular indication of having a residual stresses at the tip. So yes, I think we need to have a more collaborative research and data, because data are with us and we need to analyze them for some conclusive or let's say concrete conclusions.
Thank you. Francisco?
Yeah, I have no experience with instrumentation of the reinforcement bars. So what we do is we take the condition before pile test as the initial condition. We disregard installation effect. They probably are present, but it's not considered in the everyday practice.
Yes. Actually, during load testing, we benchmark it, the strain gauge readings and other readings at 0, and then we further analyze the thing. So all residual stresses, if any, those would be already logged in. So which you will not be able to analyze them in the pile load test, let's say, response. But if you get back and analyze holistically from the installation to lowering to, let's say, the test, probably you can get some echoes. But definitely, a bifurcation of stresses due to residual stresses and installation effect, that would be a challenge.
Thank you. And just a final question, because I know we're running late. Professor Dipankar, a tricky question. In India, the use of pile raft concept is used for routine foundations. You showed very impressive structures. In Brazil, there are some foundation engineers that use piles as settlement reducers in a concept associated to pile rafts, but in a much more, let's say, humble for residential flats, but much more humble loads applied to the foundations. Is that also used in India?
Yeah, so a very apt question and important question. Probably what I can say that the number of projects in foundation engineering, whatever in India carries out for various infrastructure, if we take the proportion, probably the combined pile raft is not used that frequently. It is used only for very specialized cases of structures and foundations where both safety and economy has to be maintained, and also for some important structure, as I have mentioned, because the main reason, what I will say, as you said, the pile used as a settlement reducer, like which is essentially that raft enhanced by pile, or pile enhanced by raft, that concept actually what UK manual suggests. So for conventional residential building, it is not that commonly used in India till now, because in India, there is another thing we have to always follow. For any infrastructure project, we have to strictly follow our Indian standard code, IS code. And you know that combined pile raft foundation, still we don't have an Indian code, because we are working on it, like in our Indian code committee. I'm also a member, and we are trying to start a new code on this combined pile raft. At present, only this international guideline gets followed and some research paper. So only for special structure where permission is given to allow to use the international practice, there only it is used. But to your answer or your colleague's answer that whether it is commonly used, answer is no, yet, not yet. So probably we look forward to have a code of on combined pile raft. Yeah, thank you.
Well, thank you all. I hand back to Professor Chaudhary to continue the session. Are we going to have an intermission or not? Please, Professor Chaudhary, lead us.
I think we don't have time for intermission. At least 5 minutes we can cover up in that manner. So we directly go to the next session, and I request Professor Sirish, are you there? Professor Sirish?
Yeah, here.
Yeah, Professor Sirish.
Professor Sahu, yeah, I'm here. Sorry.
Please go ahead and introduce the next speaker, Professor Raj Gopal.
Sure. So, very good afternoon, good evening, and good morning, friends from Brazil and India. It gives me an immense pleasure to introduce Professor Raj Gopal to this August gathering today. Professor Raj Gopal is a professor of civil engineering and PK Arvind's Institute Chair Professor at Indian Institute of Technology, Madras. He has been teaching at IIT Madras since 1993, and he has guided several doctoral and master's students in his career. And he's well known in the field of geotechnical engineering, especially geosynthetics and soft ground improvement. And he has conducted and participated in several conferences in India and abroad, and delivered keynote lectures, especially at Indian Geotechnical Society annual lecture, this very prestigious lecture in 2016. And he has been a president of Indian chapter of International Geosynthetic Society and executive committee member of International Geosynthetic Society, as well as Indian Geotechnical Society. And he's a fellow of Indian Geotechnical Society now. And yeah, so with this small background, I would like to welcome Professor Raj Gopal to deliver his lecture on soft soils and ground improvement today. Thank you very much.
Yeah, I invite Professor Raj Gopal to please deliver his.
Yeah, so thank you very much, Professor Sirish and then Professor Sahu. And it's my pleasure to make a small presentation on this occasion of Indo-Brazil webinar. I hope you are able to listen to me and see my screen.
Yes, sir. Clear, crystal clear.
Yeah, okay, good. Just checking before I proceed. So today I will be talking on the geosynthetic solutions for improvement of soft clay deposits. And before I do that, I just want to digress a little bit and continue on what Professor Sitaram talked about yesterday. And before that, let me just reminisce a little bit about my connection with Brazil. Actually, I remember my trip to Brazil to attend the International Geosynthetic Conference in 2010. And that was very well organized. I had a chance to interact with several geotechnical and geosynthetic engineers. And then the geosynthetic industry from India and Brazil, they're collaborating very closely with each other. And in Brazil only, I got inducted into the Council of the International Geosynthetic Society. So Brazil surely plays a special part in my life. And so let me come to this, and this talk will be mostly on the geosynthetics. It is not on the geotechnical aspects, but anyway, it has become a very good part of geosynthetics. So let me start. So yesterday, Professor Sitaram talked about the railways and highways and then the airports. And what you are looking at is the airport runway embankment at Sikkim, Pakyong, Sikkim. This particular embankment, it's nearly 70 meters height, and it had to overcome a lot of natural challenges, seismicity, rainfall, and so on. And to a very large extent, they were able to overcome by using geosynthetics. And very close to that is the airport runway embankment at Kannur International Airport in Kerala. Here also, the height of the embankment is nearly 70 meters. And this is mostly in the runway and safety area, because this is a tabletop airport. This is the level of the runway, and then there's a deep valley, and the runway had to be extended by about 250 meters. And this was stabilized by using geosynthetics. And the next slide, I have a small this thing. It's a snapshot. This is the long shot view of the runway embankment, and it started with gabions filled with stones, and then the reinforcement was polymeric strips, then the HDPE geomembrane, and then non-woven geotextiles, and then HDPE drainage pipes, then the coir geotextile for erosion control. I think all types of geosynthetics were used in both the projects, in both Sikkim and then in Kannur. And the design at Kannur Airport was actually through finite element analysis. That's a big improvement compared to the previous one. And so let me just take you back, and once again to Professor Sitaram. Yesterday he talked about the China Bridge. Slightly away from that, there are some railway embankments nearly 45 to 50 meters height, and these are all done in very difficult terrain. I'm not showing all the geology and other things, but they're all built using the geosynthetics, and they are designed for very high seismicity and all the other special conditions. And just to take you back about 1,000 years, and India is, it has one of the few countries that has continuous civilization for not less than 10,000 years. And so here you have a temple about 1,000 years old. The height of this temple is 220 feet. And compared to that is the Leaning Tower of Pisa, which is about 190 meters height. Both were built almost in the similar soil conditions. And then the other, I tried pushing it out, but I could not succeed. Whereas this one is still standing perfectly. And then just one more example. Yesterday we had a talk on the dams, and this particular one is about 2,000 years. It's in Indian language, we call it as Anikattu in Telugu. is actually, it's a small barrage. The kings in those days, they built about 20 feet height, 5.6 meters height barrage to irrigate the neighboring the fields. This particular one is the Kaveri River, which is the lifeline of Tamil Nadu, then Karnataka and the neighboring states. So just I thought I will give you some examples, then let me come into my talk. The brief outline is this, and let me get into the, before I start, oops, sorry, I think something, what is this happening? Okay, I think I cannot control that. See, when we deal with the soft clays, some of the problems that we have are the low bearing capacities, then very large settlements, and invariably there's going to be consolidation settlements, both total and differential. And we also have to deal with the very large lateral flows. The consequence of that, we can see here. Here is a temple that is tilted, and here this particular classic picture is from Manitoba. Here we see the two silos kissing each other. And this particular one is from India, from Kolkata. The highway embankment has undergone slip circle failure. And here there's another road that has undergone slip circle failure during the construction. And these are all happening because of the very low strength of the foundation soil. And the problems were overcome in several major projects like Airbus factory in Germany, Kansai International Airport in Osaka, Japan, Changi Airport. And then the entire Mumbai city is actually, it's founded on extremely soft clay, going up to almost 20 meters. And several islands were taken from the sea by backfilling. And now in the present scenario, we use the geosynthetics a lot. I'll just briefly give you an overview. One of the traditional solutions is the pre-consolidation or the accelerated consolidation by installing sand columns. But then the sand columns, they're not popular now because we have a much easier system, that is the installation of prefabricated vertical drains. We can easily install them and then reduce the drainage path length and then achieve accelerated consolidation in a very short time. And associated with the PVDs, we have the vacuum-induced consolidation that leads to very fast consolidation, much faster than the normal consolidation. And the advantage with the vacuum consolidation is the total stress remains constant, and the stresses are isotropic. So we will not end up with some failures that we get with normal consolidation, that is the too much of lateral flow and all those things. And in India, we had a small trial of the vacuum consolidation in Kakinada. We had a site very near to the shore. Is actually here, you can see the sea water. And this particular area was treated with vacuum consolidation on one side. And then we also treated with by normal consolidation by putting in a sand fill. And here you see the PVD that's connected to the vacuum pipeline. The system that was adopted here is the PVDs were terminated within the clay soil at about 4 meters depth below the ground level, and then the vacuum was applied. It was a very low cost project, so there was no geomembrane top layer, or there was no cutoff trends, because we were just interested in knowing whether we can connect the PVD to this vacuum pipeline and then see whether we are able to achieve some consolidation. And So here we see the time settlement data. The test was done for almost, sorry, I think this is, yeah, this is the surcharge loading, and this is the vacuum loading. The test was done for only about 1 month. And this particular one, you see the extrapolation based on the laboratory data. And some tests were done, the light cone penetrometer test. And these are the initial load tests. And these are after the consolidation for about 3 weeks. And here we see that the LCPT blows have increased a lot. Especially we are interested in the layers below the 3 meters depth, because that's the clay soil. There's a clear marked improvement in the strength of the soil. And we were able to correlate this through some laboratory tests also. I'm not going to present that because I'm going to present on some other topics for today. And here we have a geosynthetic pile raft system. This particular one is similar to our the pile raft that was presented by Professor Dipankar, except that here the raft is a flexible raft, and these piles, these are only compression elements, and the raft, in place of the concrete raft, we place only some layers of very high strength geosynthetic, either a geotextile, woven geotextile, or a geogrid. And because of that, there's a good load sharing, and we can transfer the load to very deep soil layers. And here you see one picture of the system under construction. And some tests on this were done at IIT Bombay in the centrifuge as part of my students' PhD topic. And for her, Professor Viswanathan is the co-guide at IIT Bombay. And this particular one is actually this. This is the centrifuge model, and the test was run at about I think 50 G. So the height of the embankment in prototype is about nearly 5 meters. And here I'll just show you some results. And this particular one shows the settlements during the construction for the unreinforced case. And you see very large settlement, and then a good amount of heave because of the soft clay soil. And here we have a geogrid reinforced embankment. The settlements are slightly smaller, and the ground heaving is not very much. And then comparatively, we have the pile platforms. This particular one on the left-hand side is with end-bearing piles, and this particular one is with floating piles. And here you see the settlements are very, very small compared to the previous cases. And also with the friction piles, with the floating piles, there was some settlement. And in both the cases of the end-bearing piles or the floating piles, the heaving was very much controlled because of the good load transfer. And one paper was published by us in the recent Geosynthetics International. And here we see one more example. Especially this is good for thin soil layers, thin foundation soil layers. And when your embankment is very wide, we can use a geocell, either prefabricated or the fabricated at the site. And by changing the failure mechanism, we can increase our bearing capacity from 5.14 to almost 20 times CU. That is because of the change in the failure mechanism. And here you see one application of this. Actually, this was built in Andhra across a river. This particular picture was shared with me by Professor G.V. Rao of IIT Delhi. And here you see the geocell, the aggregate in the gabions, compacted by a vibro roller. And so there's another option of granular columns. So actually in India, we use this as a stone column because mostly we use only stones. But internationally, it is called as a granular column because we can also use high strength sand. And unfortunately, the compression capacity of these columns is only about 8 times Cu, where Cu is the underlying cohesive strength of the soil. So if your soil has a very low low shear strength, your column will not have much load capacity. And so we can think of some other alternatives, and that is when the idea of encasing the columns with geosynthetics has come in. And these columns are called as encased granular columns. And I've decided to present this in more detail because there is a Brazilian connection. We had the data from Professor Almeida from Brazil, who did a lot of field tests, and we were lucky to have the data. And one of my recent PhD graduates, he spent 1 year with him as a postdoctoral fellow. And so I decided to focus more on the granular columns. So here we see the granular column encased within a tube of geosynthetic. And so because of this encasement, the granular column has a higher load capacity. Now, because of the soil, it will get some confinement. And because of the hoop tension force developed in the geosynthetic, it gets some additional confinement. And at the same time, the geosynthetic also acts as a filter and a separator layer to separate out the soft clay from the good quality granular material that we place. And here we see one example of the reclamation at Hamburg for the construction of Airbus factory. And here you see 1 meter diameter sand column fully encased in a woven geotextile. And this is the schematic. So actually this particular one is good for either sandy soils or even soft clays. We can insert a hollow pipe and then lower the lower the tube. And in fact, in India also, there's one company called Garware Wall Ropes. They introduced the seamless tube of about 600 mm diameter. We can fill it with granular material and then remove the steel pipe. And here you see one more example of the encased column. And here also you see one more example. And these columns, they can be installed in the ground in different patterns. In the triangular pattern, square, and then hexagonal pattern, and so on. And so here we can install them at different spacing to diameter ratios. And then among these three, the hexagonal pattern gives the least area replacement ratio. So in terms of the quantity of stone or the granular material that is used, a hexagonal pattern uses the least quantity of granular material. And so it is more economical to use the hexagonal pattern if we can. And by using the geosynthetic encasement, we can use the hexagonal pattern in place of triangular and then the square pattern. And there are different design methods. One is a German design method, FGO. I will not go through the details. I think basically a series of parametric studies were done to see the effect of different parameters on the settlement improvement factor. Basically, the problem with the soft clays is the settlement, and the settlement improvement factor is the factor by which the settlements are reduced. So if you have a settlement improvement factor of 4, that means that the settlements will be 4 times lesser of the untreated ground. And here on the x-axis, we have the diameter, then the different patterns. And here we have the spacing to diameter ratio, and then the constraint modulus, and then friction angle of the granular material, and then modulus of the geosynthetic encasement. And there's an IS code, IS 15284, that was proposed a long back, almost 15 years back, for the normal granular columns. And we had proposed a modification for that based on the geosynthetic encasement. And these are all the equations that are associated with this Indian code. And we can consider the additional confinement in this by use of the geosynthetic. And then, okay. And it's, here is the additional confinement delta sigma 3 that we can estimate by using the hoop strain for any given axial strain, and then the geosynthetic modulus. And here, the axial strain is the one that we can allow. And based on the conditions, we can fix the axial strain to about, let's say, 2% or 5%. Then calculate the hoop strain and then the confinement, and then we can design it. And then my student has done a number of parametric studies, and then he has come out with some design charts. And here you see the comparison with the previous charts. And I will skip all this. And how do we know what we are doing is reasonable or not? And for that, we had used the field test data that's published by Professor Almeida. He had published in a series of papers wherein about 5.5 meters height embankment was built. And these are all the granular columns, in case of granular columns. And it's a good test, because not only the settlements, but also the pore pressures, and then the lateral deformations. A lot of data was published, and we were able to calibrate our numerical models. And here you see one comparison. This particular blue line is for the field data, and the columns in the field test were installed in square pattern. And this particular one, the blue, is for the square pattern. And the data of both the field data and the finite element results, they were very closely matching. And here you see one hexagonal pattern result. And this particular hexagonal one is the equivalent one that is designed separately. And this particular one is only finite element result, which is reasonably matching up to some time. And then beyond that, there is some deviation, but then this difference in the settlement is only about less than 10%, which is not bad. So that means that with hexagonal pattern that uses much lesser stone quantity, we can come out with a design. And this particular data is that's published a long back by the Germans. And there is some data from laboratories, and then some data from field tests. And this particular dark line is for the ordinary granular columns, and these are for two different ranges of modulus of the geosynthetic. This is for a reasonably flexible geosynthetic, and this is for a very stiff geosynthetic. And this data, the green and then this orange color one, they are from the IS code and then the Geo code. They are reasonably matching. They are falling within the same range. So that means that our design methods, both by FGO and then the modified IS code method, they fall within the observed data. And we went a little bit further. I'll just take another 2 minutes. We have number of design charts, and what we posed is, let's say we want a certain settlement improvement factor. In this particular case, let's say we want 2.6. Then with hexagonal pattern, we require a diameter of about 500 mm, whereas for triangular, sorry, for square, we can have about 750 mm, and for triangular, we require about nearly 900 millimeters diameter, and then similarly for the friction angle, let's say we want the same improvement of 3.6, we can use a hexagonal pattern with 42 degrees infill friction angle, whereas with triangle we can have 34 degrees, and with square about 36 degrees. And then we did finite element analysis, and all of them, they are nearly matching. In fact, this particular one is showing the time consolidation data for different patterns, the triangular, square, and hexagonal. And so these are the settlement improvement factors obtained in different patterns. So these the advantage with the encased granular columns is more with the shear loading, because especially when you are constructing very high height embankments with steep slopes, you could expect very large lateral deformations. And here we see the advantage of the encasement. Here this particular one was with paper encasement, so it has simply sheared off, whereas with geosynthetic it has just bent, but it has not sheared off. And the advantage we get in the columns very near to the toe of the embankment, and I'll just show you some finite element results. This particular one is the deep-seated failure without any encasement, whereas with encasement, we can change this failure pattern to the toe failure pattern. And the same thing we had seen even in the centrifuge test. With ground reinforcement, we can change the pattern, like we can restrict the failure to the superstructure. And the advantage of restricting the failure to here is we can use any material that we want for constructing an embankment, whereas we don't have a choice with the ground, because that's the nature and we have to live with it. And here we see more results of the shear strain contours in the ordinary granular columns. And with the encasement, actually with encasement, the shear strains are almost 1,000 times lesser. So I think without encasement, there was very large lateral deformations, whereas with encasement, the lateral deformations were controlled to a very large extent. And I think this is all the data. Without encasement, you get very large lateral deformations. And some of this data we were able to compare with Professor Almeida's data also. And I think I'll skip all this because here we see the advantage of encasement in terms of the factor of safety, as we are increasing the area replacement ratio for the ordinary granular columns. Even with almost 25% replacement, the factor of safety is only increased to 1. And with the lower area replacement ratios, the factor of safety is even less. Whereas with encasement, we could increase the factor of safety to nearly 1.3, even with a very low replacement ratio of 8%. And because our mode of failure has changed from deep-seated to the shallow failure toe circle. So I think this may be my last. Just to conclude, we have, with the introduction of the geosynthetics, we have very large varieties of methods available for construction, as I discussed. And we have number of analytical, numerical, and experimental methods for investigating the performance. And then it's possible to construct even in extremely soft clays. For example, the clay in Hamburg, it has a cohesive strength of less than 5 kPa. And the way forward to have more confidence is to perform more full-scale field tests for better understanding the failure mechanism and improving our design methods. And in this connection, both IGS and then the Brazilian Geotechnical Society can cooperate, and we can share our experiences and then benefit by doing more research in this soft clay stabilization. So thank you very much. I think, and my thanks to several people, especially Professor Almeida for sharing the field data. And so here you see thank you in different languages from India. We have, and then obrigado for all the Brazilian friends. This is in my mother language, Dhanyavadalu. Then Nandri in Tamil Nadu. Then Dhanyavad in Hindi. So thank you very much. So I'll be glad to answer any questions later on after the next lecture is over. Okay? So thank you very much.
Okay, thank you, Professor Raj Gopal. Over to you, Professor Luis Melo.
Thank you very much, Professor Shahu. I will quickly introduce Professor Consoli again. Professor Consoli is a well-known Brazilian and international researcher on soil improvement. You're going to listen to a different perspective of soil improvement from this very interesting lecture that Professor Raj Gopal just shared with us. Professor Consoli had his PhD in Concordia, Canada, lectures at the Federal University of Rio Grande do Sul in the extreme south of Brazil, has recently been awarded or has been listed as among the 2% most influential researchers in the world, according to a list developed by Stanford University from the USA. Professor Consoli has more than 200 peer-reviewed papers, books, and is a very active consulting engineer. Professor Consoli, please, the stage is yours.
Professor Luis, I'm sorry to interrupt.
You are on mute, Nilo, you are on mute.
Professor Luis, can you please tell me with what name he is in the meeting?
Excuse me, Professor, he is on BZOB. See the screen?
Okay, I made him host. Now he can unmute.
Okay.
Okay, please go on.
Thank you very much. Yes, I'm going on now. I was disabled to do so, but now on, just to check it out, are you seeing my screen?
Yes, clearly.
Yes.
Okay, thank you very much. So I would like to thank you very much for the Indian Geotechnical Society and also Brazilian Geotechnical Society for the invitation. And so I'm going to present some of my experience on ground improvement applied to problematic soils and also tailings, I would say, in the beginning. Okay, all right. So let's start here with some research that I have done a long time ago, more than 20 years, with my colleague Gillian Sills from University of Oxford. At that time, we are worried about the disposal of tailings behind dams. Well, what we developed at that time was a numerical analysis together with field and lab analysis that took us to a good definition of the weight that it disposes and so through this control volume and in a real situation that we have had. Okay, in the end, we got to be able to simulate exactly what happened in the field regarding the voids ratio that were developed with depth and also with the width of it. And I realized at that time that it was really a material that was quite hard to deal with, because the minimum voice ratio that we have had at that time with a bauxite tailings in this case was about 3, which is quite high, and it's similar to some soft soils that we have everywhere in the world, let's say, this kind of stuff. So this is published in a Geotechnical paper from the year 2000 regarding the soil formation from tailings, and even won a Telford Prize at that time. But from then and on, I realized that I have to change my view from these soft soils or soft tailings or soft materials or loose sands and so on. Instead of adapting the solutions due to the existence of these problematic soils or tailings, the concept developed herein and from that time and on by myself and the people that work with me is adapting the soil tailing to the needs of the geotechnical and environmental engineer. In other words, I was going to search for ways of changing the mechanical characteristics and as well as the performance of these problematic soils, let's say sulfated soil, dispersive soils, highly organic soils, loose sands, and also tailings. That was the view that I have from that time. And one of the ways of doing so was to insert some amount of cement on it. For example, in this case, we can see this figure that was also published in Geotechnical now in 2014. We have different amounts of cement, and for each amount of cement, we could see small amounts of cement, you have a behavior that starts increasing the amount of cement or lime or whatever that you have, you start increasing stiffness and also strength of it. So as the strength increases, the brittleness also increases, and then that's a problem also. So in order to look at this problem of brittleness of the material due to the insertion of cement, we could try to solve it through the insertion of fibers, for example. And in here, right beside here, we can see a paper from 2008 published in Geosynthetics International that we might transform the soil from something that's practically elastic, perfectly plastic, to something that has a strain hardening kind of behavior under different amounts of confining pressures, let's say. Okay, so if we do such a thing, if you do put some cement and also some fiber, depending on the amounts that you have, you might have results that, for example, let's look to this result here. You have 0% of fiber and 4% of cement. You have some behavior that is quite stiff and then brittle, and then it comes down to a softening. But if you add to it 0.5% of fiber, besides of increasing the strength due to the fiber insertion, you also have a ductile kind of behavior. So you can try to find optimum amounts of fibers and also cements in which you increase stiffness, increase strength, and also continue with a ductile behavior, which is something quite interesting. And such a result was published in 2009 in Geotextile Geomembranes. Here, I would like to come back to the tailings failure. We see here the failure of Brumadinho, in Feijão Dam in 2019. Here, the results of the failure that we have had previously in Mariana in 2015, and the Fundão Dam. And we can see that the results are extremely bad. And looking at such let's say, such results that we have had, of course, several people are looking at solutions for it. For example, as many people has already researched about that, we have the liquefaction problem that is shown here. In this case, for some gold tailings, specifically not iron tailings, but it shows that for small confining stresses, you might have the liquefaction occurring. And in order to try to avoid that and to solve the problem, one of the things that we are studying at this moment is like to add small amounts of cement to these tailings in the place that they really are. And in this case here, adding amounts of, for example, 75 kilos per cubic meter, you might have a completely different situation from the previous one, in which the previous one without cement, you have had a possibility of liquefaction. And as well, when you just insert small amounts of cement, you have a completely different behavior, as we can see here, even with the production of negative pore pressures for in this undrained triaxial testing that we can see here. This is a paper that is being written and was submitted to publication, not accepted yet. All right, where we could use such a situation, let's say it's just an idea in this moment. Let's say that you have this upstream dam and you want to decharacterize it, or you want to turn it into a stable place. Let's say you could do such a deep mixing below the tailings that you have here in the dams that you are putting upstream, and improving it, you can stabilize it. This is just an idea that we are trying to study at this moment, but looks that you can mitigate the possibility of the potential of liquefaction and increase stability and other things through this idea. Let's go to another problem here. We have here in South America several places, and this is a case in Paraguay, but also in Bolivia and even in Brazil. We have several places where we have sulfated soils and also dispersive soils, that the use of these materials is really difficult. And in those places, it's quite common only having such a material, and they try to use as base of pavements or sub-base and so of pavements. And what we can see in this photo from a newspaper from Paraguay, what happened in some situation. They use it, and then the roads, after a few space of time, become like that. So it's not possible to go on with cars and so after rain, or even before we have this such a problems. So we have studied it, and see, you can hear at the back, sorry, at the bottom here at the right, so the problems that you have through dispersive soils that have high contents of sodium, for example, in which you have these holes. So the erosion is incredible. And besides of it, you also have, besides of this sodium, you also have sulfates, calcium sulfate, sodium sulfates, and so that also have problems or bring problems to this material. But as I said before, stones and sand and so are not available in this area. So granular material is not possible to be found in a nearby places. They are more than 400 kilometers away. So regarding economic questions, it's not viable to use. So you have to use this. And one of the ideas of using this material is to stabilize with lime, with cement, or even with some other kind of cements that you might use. And in this situation, just to have an idea regarding one of these materials that is sulfated, the amounts of soluble sulfates is about 15,000 parts per million, which is quite above the usual ones that you have. And for usual cases, it's not possible to treat it with any kind of cement. However, we went on, and in this paper here, we used the mellowing technique, and also we add some coal fly ash as a precursor together with lime and so, and we have been able to solve the problem. And we can see before here the region, what happened here without any kind of improvement. And then we published in Canadian Geotechnical Journal a test trial that we have carried out in a road section at the place where we have this soil here with the compaction and so number of passes that we have had. And then we have chosen 3 different densities in the field with different amounts of lime also. And we have done some sections, different sections with different amounts of dry unit weights and different amounts of lime. So as I said, it was published last year at Canadian Geotechnical Journal. The results of this study, here we have some lightweight deflectometer also to check it out, the stiffness that we get during the time. And here we have the results of it. For example, when we have, of course, denser compaction, let's say we get to dry unit weights, the higher that we could get through that energy, and also different amounts of lime, we show that the working between 4 and 8% of lime didn't change so much the results. But here, of course, with time, it increases the stiffness due to the cementatious that occur, the cement that's working, and so hydrates, and also the links of pozzolanic reactions that we have the lime with the soil, and then you reduce a lot the deflections with time. So this is after 1 day, and this is after 28 days of curing. So you can find this, as I said, at Canadian Geotechnical Journal. There is the reference behind here, so below here. Another thing that's quite interesting is that we have carried out tests in the lab, and also we collect specimens from the field, and we were able to see the unconfined compressive strength, how it changed with time. And here we have, let's say, after 30 days, after 60 days, after 90 days, and also after 180 days, that it was increasing with time, the strength. These results here are results from the lab, and these here are from the field. So we try to, using these results, we try to see the trend, and we saw that in the field it was even a little bit better than what it was expected to go. But it means that the mix in the field was quite well done, I would say. Here we have another kind of problematic soil, which is highly organic clays, and we have a field and lab experience with mass stabilization, which means you have here the highly organic clay, and so, and you put an embankment, and you start dealing with this improvement through mass stabilization. This is the mixer that we have, and also here in the tip of it, that makes the mixing in the field. Of course, this is quite artisanal, which means depends on the operator here to be well done, this kind of mix. This was published also now in 2020 at Journal of Materials in Civil Engineering from ASC, and it is interesting to show the lab and also the field results that we have had. Just an idea here regarding the classification of the material. The pH was quite low, like 3, about 3, and the organic matter content was about 50%, so it was highly organic. The natural water content was quite high. We can see here about 500, at least 500%, the natural water content, which was nearly the liquid limit, the material. And also the sulfate amount was high, not as high as the others that we have the sulfate, but it is also quite high. So we have tested, in this case, the possibility of the action that we have if we preload or if we do not preload the specimens, which means if you put an embankment here in the top, which it will certainly reduce the voids ratio due to this embankment. And we use without an embankment and with 1 meter of embankment, which would be a pressure of about 18 kilonewtons per cubic meter, besides of treating it with some amount of cement that we have decided to change to C. So in the lab, we have tested here, in this case, with this weight that take the pressure of 18 kilonewtons per cubic meter to simulate what would happen with 1 cubic meter of 1 meter of thickness of embankment in the top. And seems very interesting resulted from these tests in the lab with and without the preloading. We can see here that after a few space of time, we have tested the unconfined compressive strength in this here versus the amount of cement, 100, 150, and 200 kilograms per cubic meter. We have checked that without preloading, we have this kind of trend. And with 1 meter thick preload, which means 18 kilonewtons per cubic meter, we have this increase from here to here. Okay. Besides, we have measured the porosity that we have had in these specimens. So if we put a confined compressive strength that is linked to these amounts of cement without preloading and with preloading versus the confined compressive strength versus the porosity here that you have measured in the field, we can see that in the end you get to a unique trend here. However, the results without preloading, they are quite below the ones that you have the preloading that are here in the top. So you get much stronger strength and so using the preloading. So it's quite interesting to analyze such a thing and to get to such results. Here we got like specimens from the field and from the lab. And of course, that as I said before, the artisanal mix in the field, because it depends on the operator and so it's not so perfect. And so in the field, we got a strength that is about half of the strengths that we have in the lab. So these are the difficulties that we have in the field to mix. But even though it increases a lot, the strength compared to the unstabilized material that is right below here. Okay. Here are some results regarding the relation between unconfined compressive strength and the second modulus at 50% of maximum strength. And we can see here that they get such a trend that we can observe here. And these results, generally speaking, are results with and without preloading from the lab. And also here in the bottom, we have some results from the field. Then we can see that they follow a similar trend in both cases. Here is another research that was carried out at one of my sabbatical license in 2006, in this case, at the University of Western Australia. And in this case, we have carried out a test also in a centrifuge in which we have to dig some holes here and in order to put a shallow footing there, and we have backfilled it with and without some amounts of cement. And then we have tested it after some time of curing, and we can observe that in this case, the backfill was filled with cement, 1%, 3%, and 5% of cement, or without any cement. And then we have pulled it out after some period of curing, and we can observe in this case here that the results, this is a normalized force that was observed to pull it out, this shallow footing that we have here, without any cement. Then if we put 1% of cement, we double the strength the force needed to pull it out. If you put 3% of cement, you increase it by from 50 to about 170. And if you put 5% of cement, you increase even more to 250, let's say. Here are the CPT tests that we have carried out inside the centrifuge to show how was this material, this backfill strength, how it was, let's say, here in the beginning without any cement, here with 1% of cement, with 3% and with 5% of cement. Right below here, we have had like some soft soils. Then it shows that in the end, for the soft soil, it comes also to a unique result. But here, the improvement is quite massive. And this also got a prize at the TELFL Premium, in this case, from the Institute of Civil Engineers from the UK, in a joint work with Professor Lehan and Professor Richards from UWA and from Southampton, in this case. When I came back from this sabbatical and before going to another one in Bristol, it was interesting because we carried out similar tests, but in the field in real size. So we have here some backfill that we have done with cement and in different thicknesses of this, the thickness of this layer. And we could find out similar results, but in the field, confirming the results that we have had in the situation in which we found in the field without so many problems. We increased a lot And so the influence of the depth was quite well shown in this case. This was published at the Journal of Geotechnical and Environmental Engineering in 2013. Here is a paper in which we have also improved the layer and in the field, and we have seen the mechanisms of failures that we have had function of the thickness of this layer. And we have done it in the field, and we also have carried out some numerical analysis showing how it started the situation with tensile strengths. So if you put a shallow footing in the top and you loaded it, in this case where the diameter of the plate regarding the thickness here is not, let's say, the age, which is this thickness divided by the diameter of the plate is less than 0.5, we have the failure starting at the corner of the plate, which is numerically speaking through tensile strengths. And here we have seen exactly the same in the field. While in the case that this is quite thick, more than 0.5, we have the maximum tensile strength, and where it started, the situation, the failure starts in the bottom here, exactly in the middle. Once this is symmetry axis, in this case, we have seen starting in this place, as it shows here, the failure mode, which is also interesting. So this was published now in 2019 at the Journal of Geotechnical and Environmental Engineering from ASC. So at this moment, I have shown to you questions regarding, let's say, the use of cement, or if you compact or whatever. But one of the questions that we have at this moment is, couldn't we go for some more sustainable cements, for example, in order to avoid problems that we have of sustainability problems and so on, and also the economic problems of using cement, if you could use some residues that we have nearby where we are doing the works, we could reduce costs and also turn it the solution as something more viable, looking at sustainable questions and also environmental, besides of economics too. So we went after that, and there's something that we have published now in 2020, which is like the production of lime through eggshell. We have collected eggshells here, and we have produced lime through it. And here we can see some pictures showing, for example, the production of these limes. A quick lime, we have here a photomicroscopy showing how it is, how is the result when you have quick lime, or when you have hydrated lime. They have such a view in this case, which is quite interesting, that we are able to produce it with good quality. And also we have produced a cement in the end, mixing these eggshell limes and also other limes that are residues with ground glass. So this by itself is a new binder, and we have it published now in 2019, also in Journal of Materials in Civil Engineering. This topic here we show the X-ray diffractometer, showing that in the end you get tobermorite, which is the same result that you get if you use Portland cement, for example. Here are the results that we have, like the unconfined compressive strengths using this kind of cement with a sand, for example, just in a small period of time. We have got some good results that can be used in the field for the improvement using this lime, or even other limes that are residuals, like such as the carbide lime, for example. And this was published at also the Journal of Geotechnical and Environmental Engineering, as you can see here in the bottom. Here is also another paper that was published in the Journal of Geotechnical and Environmental Engineering in 2020, in which we have improved in the field certain volumes, and we have put some steel plates on the top, and these would be some improved layers in order to increase the capacity of this plate load test in the top of it. And we see even the failures. And so with some, in here, what is interesting is that the cement that was used specifically was carbide lime together with ground glass. So two residues that were turned into cement, and we improve different areas and regions to check it out, what was going to be the effective kind of failure mechanism that we would have in each one of these cases. Here, just to show some quite ancient also result from 2001, when we have published the behavior of soil mixed with coal fly ash and carbide lime, so both residues. And we can see here, if you just have the soil, if you have soil with 4% of carbide lime, if you have something stiffer, but if you put some fly ash and the carbide lime, then you have a very good situation in which the pozzolanic reactions are excelled in this case, and you can get quite nice results. Something very interesting here that is also important to anyone that is going to work with soil stabilization with cements and so different cements, we found out a way of controlling and even to get a dosage of any kind of cement when you are blending it with soils. And we realized after a long period of research that there is a parameter that we call in the end porosity divided by volumetric cement content, which is in the end equal to the volume of voids divided by the volume of cement. But even though it's better to publish in this, because this is without any unit and this has units. So if you use this, it will depend in the unit that you are working with. This paper was published in 2007, and up to nowadays, it was published in Journal Geotechnical and Environmental Engineering. It has more than 250 citations in Scopus and 220 citations at Web of Science. So it was quite well cited. And from this initial study, we got plenty of studies on dosage showing that it works. Let's say in the first case here, in this paper, we see here that we have worked with different dry unit weights we have here, and also different moisture contents and several amounts of Portland cement from 1 to 7%. And so we have the results. But if we put the unconfined compressive strength got from all these results here versus this parameter here, that is in here, we get a unique curve. Okay, so we are working in volume, and which means that this parameter controls the strength, unconfined compressive strength of this cemented soil with Portland cement in this case. Here in 2017, so up to this case, this moment in 2017 and a few years later, we have seen this concept in the lab and also from specimens got from the field. But we just developed an analytical solution showing that this is true in 2017, after a period that I have been to Bristol and in which I've been working with Professor Giambra and Professor Ibrahim. And so we have been able to develop analytical solutions showing that really this parameter controls the strength, but in a first analysis, it controls the unconfined compressive strength. But then we have shown in the lab and also from the analytical viewpoint that it controls also the tensile strength. So this porosity cement ratio or porosity cement index, whatever is the name that you see, it controls completely. Here we have the results of different amounts of cement and different densities, and all of them, they fit in a unique curve for unconfined compressive strength. And here we have another curve for tensile strength. And besides of it, both get equations in which this part here is the same. So the only difference from tensile and tensile strength and compressive strength is a scalar in front of it. So if we divide QT by QU, which means tensile by compressive, we get to a scalar. And this scalar, of course, depends on the cement, on the soil, and so. So in this case, for this cement and this soil, it was 0.15. But you might have some different values varying from 0.10 to 0.18, depending on the soil and the cement that you use. So this was published also in Journal of Geotechnical and Environmental Engineering in 2010. So we got similar trends for treating the soil with lime. In this case here, we have different densities and different amounts of lime. And when you use I just put volume of void by volume of lime, which would be the same, like porosity divided by the volumetric lime content in this case, we also get a unique curve here for this. This was published in the Journal of Materials in Civil Engineering. We published also in Geotechnical in 2012 a paper showing that the stiffness also was going to be controlled by this dosage parameter here. So G naught, which is the shear stiffness, the initial and maximum shear stiffness, we can get for two different soils that they have for a given soil, a given cement, but varying the density and varying the amount of cement that you have a unique curve for which one of these soils, which is, as I said, quite interesting. A soil from Portugal and a soil from Brazil. We have tested both with different cements and with different dry unit weights, each one for that they have, and we have shown that in this paper from Geotechnical. Another thing that from that time we showed also that we have carried out tests, triaxial tests, and we published in 2009 that if you get a unique porosity divided by cement, volumetric cement content, and you might get this value here through different dosages, which means you might have a unique value, but you get this value through different amounts of porosity and different amounts of cement. And in this case here, the volumetric volume of voids by volume of cement was 10 in these two specimens with a void ratio of 0.7 or 0.8 and with two different amounts of cement, but the ratio volume of void by volume of cement is the same. And in this case was with a confining pressure of 400 kPa. And we can see that the stress strain that we have in this case is quite similar, which means that it also controls this ratio. It also controls the stress strain behavior of it, which is also interesting. Here's a paper from 2017 in which we have shown different granular materials with different shapes, different angulosities, different roughness. Some are like quite angular, some are round, well, some are rough, some are less, quite not rough at all. And from different places in the world and from different origins, 4 of them. And what is interesting, let's say this is just KU, which is unconfined compressive strain by the amount of cement in this case. And we have tested different periods of curing, different cements and different soils, and also different amounts of the different cements and different densities too. And for each one of the soils, we have got some trend that we could see here, that in some way, this part, which is eta CIV elevated to a power here, this power is quite similar, which means this is our lab tests, and we could use a unique value here for results of different soils like Osório sand or a granitic sand, and different types of cement, which is the original Portland cement, and this is the high strength cement, and results of compression and also tension, and curing periods of 7 and 28. So the results are in here, but if we divided each one of these cures by one of the results of eta CIV, for example, in this case, I get eta CIV 20 here. So I drop in here and I divide all the curve, all this green curve by this result here. So for the same 20, I get to the red one and I got the result here, and I divide all the curve by this value. And so I do the same for the blue and the pink one. When I do that for all the tests, I get a unique curve, which means this curve has a unique eta CIV with a value of a power 1.38 that it works for all the specimens of soils, granular soils that we have tested with different roughness, different angularities, different amounts of cement for tensile and compressive strength, different curing time. And so the shape of it is unique, which is quite important. So which means that if I, in such a way, the only difference that we are going to have from the different soils is a scalar in front of it, because the shape of the curve is the same. From the practical viewpoint, if you have one point, if you do one test, you can have the whole shape, the whole curve. That's the idea. So we have carried out that for granular materials and also for soft soils and fine grain soils, including the London clay, because one of my colleagues was from the University College London and he tested London clay with cement and such and so, and organic clays and silty soils and dispersive soils and so much other materials. And also we got a unique curve here for these fine grain soils with cement. Here, as I told you, in one case, for example, getting this curve here that we get, and with one result that we would have in any other fine grain soil. For example, in this case, we got this result here. With this result, I could apply to this curve here and draw the whole curve. And this curve is based just in this result here. And we have all the other results here from the lab showing that it fits perfectly what has happened. The same here, we have got just some coal fly ash, and we have done first one test here, and with one test substituting it in this equation here, we got to draw this line. And these results were carried out later on, showing that it fits perfectly. So in this case, I could carry out just one test. Of course, we don't do just one, we do 3 specimens at the same time in order to get an average here, and then we can fit the whole curve without having to carry out dozens of tests, let's say. Well, in here, it was one of the first studies that we have carried out with a tailing, from a gold tailing in this case, that, of course, in this case, it is non-plastic. Here we have mainly silt, 71% of silt, 28% of fine sand, and then it's classified as a silt with sand, which is quite usual. However, it's interesting to call out that these gold tailings, it has important amounts of cyanide and important amounts of arsenic. So if you put it just as it is in the nature, let's say if you want to do embankment with it, you might have the pollution of the whole place due to the cyanide and this arsenic that you have mixed with it. So you have to be quite careful to that. And in this case, we decided to deal with dealing with inserting some amount of cement, and we have studied, and this is what was published in 2019 at Canadian Geotechnical Journal. We studied the durability, the strength and stiffness of these mixes. And then we can see here through the same index that we developed, that it controls the whole situation. Let's say the unconfined compressive strength changes in this way and through this equation here towards this. So once again, if you have one point, you can draw the whole curve. Also, the stiffness, the initial stiffness is also a scalar here that also is controlled by this index. And finally, something that's new at this moment, and it was the first time that we have shown that, is that you have the accumulated loss of mass from a durability dry and wet testing that you have in ASTM and several other standards, that you also control the loss of mass after 3 cycles, 6, 9, and 12, that is maximum. We have the loss of mass controlled by also this parameter. So I've shown up to this moment that this parameter can control for cemented soils strength, stiffness, and also durability of the material, which is quite important. Here we have used a similar study, but in this study here, we have used durability test, and so with a green cement, which means like the carbide lime in this case with ground glass. And also we have had similar, so this is the result for specimens with different amounts of ground glass, different amounts of lime, and different dry unit weights. And we have a unique curve here. Here we have similar results also with this same index for strength and for two different materials, showing that it also controls this material for that. Here is just going to end it. Let's say we have some other kinds of sustainable cements using rice husk ash, using ground glass, but also using bottom ash and using also some other materials like ground construction materials, let's say, that you ground them and use as a pozzolan. This was published now in Transportation Geotechnique this year. We have that it controls the loss of mass in this case, also unconfined compressive strength that I said before, and also the stiffness. Going a little bit further, this is really the last thing that we have done is also the swelling of a material of a soil that has, let's say, some amounts of expensive minerals. It also is controlled by this same index. In this case here, we have treated one soil that was expensive with lime, and we have shown here different amounts of lime, different densities that we have had, and we would control. You have a unique result based on porosity lime content, and then we have the vertical swelling of it. We have tested getting from the literature from other periods results that the people have had, and then we have shown that it controls completely. Each one has a given result, but a unique curve shape of curves for each one. But if you divide each curve, as I have done before, by the value of eta CIV that you get, the expansion in here, you can have from this all doing this this kind of test that dividing the whole curve by one value that you get here, you get a unique curve once again. This works for lime treatment, and also we have shown here that it works also for cement treatment. This was published at Journal Geotechnical and Environmental Engineering in 2020, and this was just published at Canadian Geotechnical Journal now in 2021. Just to finish it really in this moment, we show also that regarding life cycle analysis and so sustainability, we can see that if you do a mix in which you could get a unique result of strength, in one side, decreasing or using the smaller amount of lime, for example, and the densest way to get the result, or something that not compact too much, but adding some amount of higher amount of lime. In terms of sustainability, this one here, which is the one that you use a higher amount of lime and not so much energy, it has problems regarding embodied energy and global warming. So in this case here, we show in the end that if you can choose between adding more cement or compacting more, in terms of sustainability, is always better if you use smaller amounts of lime and compact it more. So that was published at Journal of Cleaner Production in 2016. And also from an economical viewpoint, we have shown similar results, and it was published now in 2021 at the Journal of Materials in Civil Engineering. So here you have seen a few papers that we have published in the last 3 years that you can check papers that you might have interest in this sustainability and so in several journals, different journals that we have had, including Geotechnique, Journal Geotechnical and Environmental Engineering, Canadian Geotechnical Journal, Road Materials and Pavement Design, and so on. So there are several. So just to finish, thank you very much. Muito obrigado.
Okay, thank you. Thank you so much. Professor Luis, you are muted. Professor Luis, you are muted. Please unmute.
Okay, thank you for allowing me. Thank you, Professor Consoli, for sharing with the Indian colleagues as well with the Brazilian colleagues cross-section of your recent research. I'm sure we have learned a lot and we may have interesting questions. I handle the beginning of the questions to my colleague, Professor Choudhury.
Yeah, so this first question is by Jayalakshmi to Professor Raj Gopal. So Professor Raj Gopal, the first question is to you. Is there any geosynthetic solution to control swelling and shrinkage in black cotton soft clay? So we'll appreciate if you be brief in answering so that we can take more questions.
Yeah, actually it is, there are different solutions, but better than, I don't know, like people have tried using a geomembrane to cut off the water supply. That's probably the best solution, but then there are other better solutions like lime treatment for expansive clays.
So second question, I would request Nitin Tiwari to please pose to Professor Raj Gopal.
Thank you, Professor Saud. Professor Raj Gupta, the question is there has been some failure in Gabion Ball at Pokyan Airport, Sikkim, and inspection was done by CBRI, Roorkee. Is there a design limit to height of a Gabion Ball? If so, how to make such wall practically possible while taking maximum allowable tensile strength of geotextile reinforcement?
Yeah, actually,
this question was asked by Chandan Ghosh, sir.
Yeah, I've seen that question. So actually, there is a local failure, and that is mainly because of the loss of fines due to drainage and filtration issues. It has nothing to do with the wall, because the wall itself is standing, but there are some local patches where the filter media has failed. So that was the reason. And then to coming back to the second part of the question, there is no theoretical limit to the height that we can build. But only thing is there are other practical issues of the lateral deformation and then the drainage, filtration. But theoretically, there is no limit. We can go up to any height. And within India itself, 70 meters has become very common, like 70 meters is the maximum height. And there are several walls that are built up to about 40, 45 meters. And 20 meters, they are very common. Like, in fact, there are several embankments that are about 10 to 15 meters height.
So, Professor Luis, handing over to you.
Professor Choudhury, I think we'll keep this pattern that we used in the first presentation. So I'll ask Professor Raj Gopal how the contribution of the geotextile encased column to the safety factor is considered in routine limit equilibrium analysis on embankment of soft soils. Would you have a contribution to share?
Yes, actually, that's a philosophical question that requires more analysis. And we can include the limit factors to bring in the reliability also into the design that I have not presented, but that some students have done. It's very difficult to answer within a short time. But yeah, that's a very good question, but that requires more time to answer.
Okay. We wait to, if you publish a paper or something, please let everybody know.
Yeah.
I would have a question also with related to the vacuum applied to what is called a drain to drain method, which you showed on one of your images. There is the Menard type of solution with blankets encased on diaphragm walls, but there's also the drain-to-drain method. Would you have any comments on the detail of the drain-to-drain coupling on top of the drain? And have you measured efficiency of the vacuum as applied with relation to that system?
Yeah, actually we tried measuring, but unfortunately all our pore pressure cells, they got clogged within no time. So we did not get much measurements, but the coupling was, we had to fabricate a coupler and connect this thing, but when we tested in the lab, there was not much of leakage, but I'm not sure about the field, because although we put in some pore pressure cells, but we could not get much out of the pore pressure cells. So unfortunately, I'm not able to comment on how efficient the system was. But at least our light cone penetrometer tests, they've shown significant improvement in the number of blows. Within about 3 weeks, our number of blows have increased almost by 2 to 2.5 times. That's the only data that we had.
Okay, Professor Chaudhary, now I'll handle back to you and we go on to ask Professor Consoli some questions, I understand.
Sure. So Professor Consoli, we have 2 questions for you. The first is, do you have any guidelines on the use of fiber reinforced soils in the field and its performance in practice?
Oh, yes. The reality that in the beginning we have had so much problems in the mix to be carried out in the field. Nowadays, we have solved that using some, in this case specifically, that we are working with some polypropylene fibers that they have a diameter that is about 0.1 millimeter, and the length not larger than 50 millimeters. They are, in this case, they are stiff enough in order not to tangle, and so you are able to mix it without tangling. And this was the solution for the situation. We have some equipments that they mix, for example, the fibers as well. They mix cement on it, not like in a way that they are big equipments, but the way of solving the problem regarding tangling was to use some fibers that they were not so much thin, but they have at least 0.1 millimeter diameter and maximum 50 millimeters length. We have been able to do such a mix in the field with success, let's say.
Okay, thank you. Second question I have, Professor Babu, Shivkumar Babu, to you. The question is, we have a lot of organic deposits in India. How is the performance of cement stabilization on organic deposits in field? What happens to wide volume loss due to organic fraction?
Well, really, in this case that I showed to you in this presentation, it's a real case that was in Rio de Janeiro, in which we have at least 50% of organic matter that will decay with time. So it will like rotten and so. And the situation is already bad because we already have a very acidic environment. But in order to deal with that, you have several let's say, ways of doing. In the present case, already really small, not small, but let's say 125 kilograms per cubic meter of cement was able to deal with all the chemical questions, increasing the pH to let's say not acidic, but when it's alkaline, exactly, alkaline environment. And in this situation, it was already enough in order to get the hydration to occur, let's say. So there are some cases in which the acidity is so high that you have to enlarge the amount of cement even more just to alkalinize the environment. That's the question. And regarding this decay that you have, you already are not counting with it because it is not going to get stiff or whatever, this material. It will decay and disappear with time. So if you are able to resolve the problem in a short space of time, once you have the decay of this material, technically speaking, it might have a problem if you get it quite acidic once again, which will destroy the cementitious things that you have. So it still needs further studies for long period of times. So the question is how long the cementation will be held in there if you continue having the decay and acidifying the environment. This is something that's not solved yet, but for usual period of times, it's not a problem. Let's say longer periods it might be, but as I said, you need to study a little bit further.
Thank you, Professor Consoli. Over to you, Professor Luis.
Okay. I have a question, Professor Gonzalez, with relation to highly organic content on clays. Even though there is a gain of shear strength, and due to the fact of its high porosity, its high void ratio, this material may be susceptible to volumetric collapse, a significant, important volumetric collapse, in case it reaches high stresses close to failure. How would you recommend that we deal with this topic?
Well, inserting a nice factor of safety, not to reach nearly this failure problem. That's it. Of course, you are going to stiffen the material. You are going to strengthen the material, but you have limits, and these limits are not going to be too high. So you have limits to apply such stresses that cannot be near the failure one in order not to have problems in the future. As simple as that.
The other question is mine. I have faced, and my Indian colleagues were probably going to see this as peculiar, very acidic organic soils, not only because of organic matter decaying from vegetation, but in a case that failed in the coast of Brazil for a sewage plant, which we had to excavate, that it was farmland, and it was where the farmer used to put salt for the cattle. And so the cattle would urinate a lot on that area, and the acidity of the soft clay was exceptionally high at that place. So we had a lot of problem to treat that organic clay, not only because of the requirement of high dosage of cement, but also because we needed to introduce air. We needed to oxidize the mixture. Do you have some research? Do you have some information or thoughts on that, Nilo?
Look, in any case, when you have some specific material, you have to look at the chemistry of it and ways of dealing with that. So each one of them, you have to study from a chemical viewpoint what can be done in order to, as you say, if it's so much acidic, if it has so much sodium, or if you have any kind of stuff, what kind of chemical material you can insert in order to deal with that and be able in the end to get it stabilized. So one question that was until, let's say, 10, 20 years ago, they used to say that there were some materials that were not treatable. Nowadays, I can tell you all materials, all soils and so are treatable. It's a question of the material that you are going to use and the amounts of material that you're going to use. So the civil engineer is not so used to chemistry, and we need some knowledge on that, and we need some search in that area in order to realize what kind of solution you can have for that specific problem. So you have to go for some higher search, let's say, towards the amounts of materials that you have and the possibilities that you have in order to stabilize it. But I can tell you one thing for sure. If there is a problem, there is a solution. It's a question of study a little bit further that we use as civil engineers, that we are used, for example, usually people are like, they work like alchemists. Oh, let's try this, let's try that. Before going for such a situation, you can do something quite faster if you study the chemical amounts and what you have and so, and then you might go further from let's say, some thoughts about what kind of materials you can insert that are going to work in that situation.
Linking your answer to the next question, would you comment on the difficulties of mechanically providing a homogeneous mixture at the field in a work site? Because there is a lot of difference between, of course, lab research and, you know, putting together a mechanical procedure that develops a homogeneous mixture for the wide range of solutions that chemically we may be pursuing.
Let's say if you're interested in doing an embankment, for example, okay, with some soil that you're going to mix to something. We already have equipments that can work up to 900 tons per hour of a mix. So the idea of mixing in the field with discs and so that are going to being pulled by some equipment or so is something from the past, I would say. Nowadays, you have some specific mixers that can do that in high amounts and quite well mixed. So the solution for that is having specific equipments that can do that industrially. You can bring it to the field and it's going to do with a solution of about 900 tons per hour. Okay, so you can get something that's good enough. If it's so huge, your place, and so you can put 2 or 3 of this in order to have really large, huge amounts. But we already do have solutions for that nowadays. For these mixings, these blends that are done, let's say, internally to silos and so. No, it's not exactly a silo, but it's a complete equipment. For example, one that I was dealing a few days ago, it has 24 meters of length, but it's on the top of a truck and so that you insert in one top and it exits to the other, the mix quite well done, and it gets to 900 tons per hour. This is a solution.
Okay. Thank you, Professor Consoli. I hand over back to you, Professor Chaudhary.
Thank you, Professor Luis. And I thank all our speakers of today. In first session, Professor Deepankar Choudhury, Dr. J. Shukla, Professor F.R. Lopez, Professor Santa Maria, then the second session of today, Professor Raj Gopal and Professor N.C. Consoli presented great lectures and great information in their lecture. So I thank them profusely for giving us such great information. And I also thank all our audiences, both in Brazil and in India, for very patient hearing and asking so many very knowledgeable questions. And I also thank Professor Luis de Mello for such a wonderful coordination with me in conducting all these sessions. If you want to say a few words, Luis de Mello, and
just my closing remarks would be, and I'll start from the end. I thank you very much, the Indian audience, the Brazilian audience. It's a pleasure for me to be close to part of my roots. As you know, my father was born in India. And so part of my roots, and, you know, very nice atmosphere, very warm friendship throughout. I thank the speakers, both from India, my good friend, Professor Deepankar Choudhury, and Professor Raj Gopal, who I have not had the privilege to meet, but also thank you, Professor Francisco Lopez, Professor Paulo Santamaria, and Professor Nilo Consoli. And I thank you all our friends from the Indian Geotechnical Societies and the Brazilian Soil Mechanics and Geotechnical Engineering Society. Have a good evening in India, a good lunch, bom almoço to all in Brazil, and I'll be here tomorrow morning looking forward the third day of our webinar.
good day and good night to everyone.
Thank you very much.
Thank you.
Thanks.
Thank you.
Thank you.
So we close this session with this. Thank you. We close this session with this. Thank you very much.
So long. See you tomorrow.
See you tomorrow.
Yeah, see you tomorrow. See you tomorrow.
See you tomorrow, Professor Babu.
Yeah, wonderful, wonderful program. Thank you, Professor Consoli. Thank you, Professor Fernando. Fantastic job. Thank you so much.
Okay, bye.
Thank you. See you tomorrow. Yeah. Goodbye.